So, yeah, let
Recording
me
in
click
progress.
on accepting this. Got it. Yeah, so it's a great pleasure to welcome Ubiratã Alves to give his presentation at Eicefala. Ubiratã Alves is a lecturer, maybe going towards a professor from URGS. And he is, I was talking about Zilke's generation yesterday, and Beta is one of these younger generation and older. And Beta wrote to me when he was doing his master's, and we started interacting. He wrote to me, sent me an email asking for things. And then he was working with OT, very formal analysis. And then he moved on and he started working. He always worked with L2. I think your interest always been L2. But he moved to more experimental phonology. And then we got closer and talking more, and we've seen more of each other in the past few years. And Beta is also, he started working with L2 English, but he's also worked with Spanish, Latin American Spanish, L2, both ways, Brazilian Portuguese and Spanish speakers learning L2. So he's also, his students, lots of his students are now lecturers at good Brazilian universities. So, Beta, you developed your career in a very, very amazing way, and I'm very pleased you accepted our invitation to talk about one for all, all for one, on process-oriented approaches to multilingual phonetic phonological development. And I'm really looking forward to listen to your talk. The word's yours now.
Thank you, Thais, for this very nice introduction. First of all, I would like to, let me just share my screen here, okay? I would like to thank you for the invitation, for having the opportunity to be talking to you, to be once again part of the Eicefala team. I think this convention has, in the last 10 years, been one of the greatest conventions in the L2 acquisition field. So I'm very glad to be here once again. Well, today I'm gonna present my paper called One for All for One. And I had the collaboration of Laura Schereschewsky, who's just finished her master's degree, and Anderson Santana, who is my undergraduate research assistant. So the goals of my presentation. First of all, I would like to provide empirical evidence to the interconnectedness of languages in multi-language systems. And I would also like to discuss the importance of longitudinal, process-oriented approaches to language development. So previous research on language development has shown an interconnection of all the languages in the multilingual system. So all the languages, first, second, third, and fourth, according to Flagey, they share a common phonological space, okay? This assumption defies that traditional account in which the first language would affect the second language, and then the second language would affect the third language in a linear order of influence. As we know nowadays, the changes in any of the language subsystems may have an impact on all of the others. So the second language may be affecting both the first and the third one. The third language will be affecting the second language, and so on and so forth, right? This also reinforces the importance of a complex, dynamic approach to language development, since the first language itself shows changes over time. So under a complex dynamic account, we are always living through a development. We are always in development. Language development never stops, okay? So this said, we conclude that not only are the second and third language subsystems subject to change, but the first language itself is also subject to change. And there are many studies on that, showing empirical data on language attrition or language drift. In this presentation, I'm not going to be making a distinction between these two terms. What is very important to show is that this is a likely possibility in both dominant and non-dominant L2 environments. Okay, generally the literature shows some evidence of language drift or attrition, considering participant subjects who moved to a foreign country. But recent research, especially here in a Brazilian scenario, has shown that even if you haven't traveled abroad, your first language may be affected by an additional language system. Okay, we have many studies on showing evidence, especially teachers to be or language teachers, foreign language teachers, who also show some degree of L1 changes, right? Under a complex dynamic systems perspective, language development is a continuous process, as I have already said. Okay, and it's characterized by developmental changes in time. If this is a continuous process, we need new methodologies for data analysis. We have to invest more on longitudinal analysis, which focus more on an individual's development process, right? Based on that, Lowy 2017 proposed the difference between product versus process-oriented approaches. Product-oriented approaches are those approaches that focus on a specific point in time, as if they were like a photograph of a moment in time. And they focus on large groups, on more than one individual, so on and so forth. And they're more like traditional accounts of language acquisition. On the other hand, process-oriented approaches, they focus on a single individual or on more individuals, but taking analyzed as single units. And they try to focus on language development as a continuous process over time. So we would need dense data. We would also need data that's collected longitudinally through months, years, decades, so on and so forth. Of course, this is a challenge, especially in the Brazilian scenario, right? Lowy also says that product and process-oriented approaches, they are complementary. I mean, there are some things that only product-oriented approaches are going to show, and there are other things that only process-oriented accounts are going to show. So they complement each other. In this presentation, I'm going to be focusing on process-oriented approaches to language development, right? When it comes to longitudinal data, there are many ways of analyzing and many, I would say, recent ways of analyzing these data in the L2 development scenario. From these many different methodologies that have been proposed in the last 5 years, some of them that we have been carrying out research on are variability in peak analysis with Monte Carlo simulations, moving correlations, and change point analysis. Today, I'm going to focus on the first one, variability and peak analysis with Monte Carlo simulations. And on Friday, Laura is going to focus on change point analysis. She's going to be discussing part of this very same data, but with this other method for analyzing data. And it's very interesting because since this, at least in our country, is very recent, one of the goals that we have as researchers is to try and discuss the impact of these different methodologies on the understanding of language development data. So when it comes to peak analysis with Monte Carlo simulations, a very fundamental construct in complex dynamic systems theory is variability. Okay, this is still a preprint. It was published like 1 or 2 months ago, but I was very attracted to this article because of the title, which says that variability in CDST is just like apple pie. It's normal as apple pie. Why do the authors say that? They're actually saying that they're using this metaphor because generally, even if you're a very competent, a very experienced baker, okay, and you have already baked many apple pies, although they're all apple pies, they are never exactly the same. Those who cook will understand what I mean. They're all apple pies, but at the same time, sometimes we have the impression, today I have the impression that I follow the same recipe, but the food seems to be better, or I did something wrong. Today it's not good. All right. So what they're trying to say is that language varies. Okay. And although we may have the same categories, and actually we may have the same individual, intra-individual variability is a key concept in language development. Not only because it's part of the system, but because it will also indicate that development might be taking place, that new phases are being reached, that there is space for phase shifts. So I'm going to take the liberty to read part of this abstract, the part that I think is the most interesting thing after the apple pie factor. So phases of increased variability in linguistic constructions are often assigned that the learner is trying out different constructions. And as such, variability can be evidence for change, and change can be learning. Also, a limited degree of variability is inherent in automatic and control processes. Conversely, the absence of variability is likely to show that no learning is going on, or the system is frozen. So variability is a key process for language development. Actually, in CDST terms, variability is indicative of phase shifts. As Hepford would say, phase shifts, also referred to as phase transitions or bifurcations, were first introduced into second language development studies in the 1990s as a notable feature of CDST research. Phase shifts occur when a change in the learner's output system results in fluctuation between their initial state, the current language pattern, and a new attractor state, the new language pattern, creating a period of instability. The new attractor is not necessarily something new to learners. It could be a language form that they are exposed to regularly but have not had the cognitive ability to adapt to, or an event that pushes the learner to adapt and self-organize, resulting in using a new form. So variability is a key factor in CDST. And what we're going to do today is to search for variability in our longitudinal data. Okay, so in the studies presented today, first of all, in the studies presented today, we aim to find significant developmental jumps triggered by instruction in the additional languages. So I'm going to be working with multilingual systems with 3 language subsystems. And the first thing that we want to see is if there are going to be developmental jumps, sudden jumps, because these sudden, abrupt jumps may be indicating that a process is starting to take place, okay? How are we going to do that? We're going to try to push our learners. We're going to try to make these systems change by providing them with explicit instruction. That's a way of trying to force them to shake up the system a little bit. Well, having found differences in the second language system or in the third language system, we aim to see whether there are also significant peaks or sudden jumps in the first language system as well, okay? At first, traditionally speaking, first language systems would not be subject to these abrupt changes, to these developmental jumps all of a sudden, because they should be more stable. But our expectation is that language instruction should shake up the L2 and L3 systems, and as a consequence, later on, maybe, shake up the first language system, or at least cause some changes to the first language system. Then we would have evidence that, okay, the first language system is also subject to change, and it's adaptable according to the changes found in the second and in the third language systems, right? For that, we're going to be presenting two different studies. The first one was the master's thesis by Schereschewsky, 2021. In her study, she investigated the development of VOT patterns by Brazilian learners of English as a second language and French as a third language, okay? And she provided learners with instruction, phonetic-phonological instruction, in their second language. As you know, English has a long lag VOT, and Brazilian learners do not tend to realize that. So she provided them with information and aspirations so that they could show changes in the second language, and then we would try to see what happened in the first and third languages, which don't present long lag VOTs in word initial position, right? She studied 5 participants, but I'm going to concentrate on just one here, right? Secondly, we're going to concentrate on some data that I have with Anderson Santana, and these data are on vowels. We're going to be investigating the development of vowel patterns by an Argentinian learner of English as a second language, and Brazilian Portuguese as a third language, but this participant has been living in Brazil. Okay, so he's been living in Brazil now for 5 years. And in this case, we provided him with instruction on Brazilian Portuguese, that is, on his third language system, but which is more active than his second one. As for the methodology, we had longitudinal data. In the first study, 12 data points. I'm going to explain that later. In the second one, 24 data points. And in order for us to find these significant peaks, we did resamplings with Monte Carlo simulations. We followed this manual written by Van Dijk, Verspoor, and Lowy, 2011, in which they're going to be providing some information on how to carry out research with Monte Carlo simulations and L2 data. This was done in Excel with pop tools installed. And we always had, whenever we had a data point, we always had, each data point was the moving average of 2 data collections. What do I mean? We didn't want, to have just the data from one single collection, because maybe on that day something happened. So we always had, moving averages, so that in case there was some sort of random or totally random change, that would not be selected as a significant peak, or that would not be misunderstood as some sort of developmental jump, right? We also had a time window of 6 data points, not more than that, because once again, we want to find sudden jumps, right? So abrupt jumps. So the smaller the time window, the better, right? And we also had 10,000 reshufflings. What does that mean? We had our data, right? We found the distances between the data points from the moving averages, and then we selected one of, the largest difference between one data point and the other, and that would be considered to be a peak, right? An ascending or descending peak. Then we would reshuffle those data 10,000 times in order to see how many times that value that largest value would be achieved, okay? If it were an uncommon value, we would consider it to be a significant peak, right? If it were a common value, if it were repeated many, many times, that would be just some sort of non-significant variation that would not be considered to be a developmental jump, right? So Hepford is going to explain that Monte Carlo simulations calculate an algorithm that tests different possible outcomes for the same set of data. In our case, 10,000 simulations, and the calculation indicates the likelihood of the result appearing multiple times. So the fewer times it appears, the more significant this peak is going to be considered. As for our first study then, by Schereschewsky 2021, we're gonna concentrate on a female participant who was 24 years old at the time of data collection. She was a graduate student, and although French is her third language, she works as a French teacher, so French is her dominant additional language, okay? In terms of language proficiency, she took a self-evaluation questionnaire and she graded herself with a 6 in English and 10 in French, because she's a French teacher. We had 12 weekly data collections in each one of the languages, right? Each data collection consisted of reading aloud target words initiated by one of the plosives. And instruction on English pronunciation was provided from weeks 4 to 9. This is what Hiver and Alhuri are going to call the AXA method. So we have some data collections first before instruction, in which that's A, in which we would expect not to find many abrupt changes. Then there is instruction that's going to shake up the system, and then that's X. And after instruction is over, we have the same amount of weeks that we had beforehand as A again, in order to see what will happen to the system. If it will go back to the previous stage, it will keep on, shaking, if it will find another pattern, so on and so forth. As for her data collection instruments, she had, of course, 3 reading tasks, each one in one of the languages. They did not read the same tasks at the same time, at least one in the morning, and another one in the afternoon, the other one in the evening or on the following day, all right? It's important to say that the Brazilian Portuguese and English instruments are the same ones used in Kupski 2016, because we wanted to have this sort of comparison with some previous studies, and especially with native speakers data. Of course, since there were weekly collections, the target words were always presented in different presentation orders and with different distractor words on each week, all right? And in this study, we concentrated not only on mean VOT values, but also on minimum and maximum VOT values in each one of the data collections. Because once again, in each one of the data collections, we expected to find, a lot of variation. So as for her data here, we're starting from presenting a graph with the initial state. What are we considering to be the initial state here? The initial state should be what we found on the first data collection, right? And here where it says referência in Portuguese, that's from her dissertation, which means reference. That's the data that we have from native speakers of English who read the same instrument, right? So what we can see is that even in the first collection, right, VOT values in English approached native speakers' values. So when we got this participant, she was already aspirating word initial plosives in English, right? Interesting. It's interesting to say that as for French, even in the first data collection, we also had longer VOT values for French. So she was showing some signs of drift right from the first collection, right? Well, what is important to say is that I'm returning to English now, that even though this participant had already reached native-like patterns in the first collection, we can notice that throughout all the collections, we can see that on the right, that VOT values tend to get even higher, especially when it gets to the export, when this participant is receiving instruction, right? In French, same thing, initial stage, this participant is showing, that her French is somehow affected in a way, right? But there's a lot of variation, and we have to see whether this variation is significant or not. As for Brazilian Portuguese, which also shows a short lag VOT, we can notice that, even from the first data collection, there were high VOT values compared, especially for pa and ta, compared to those presented by native speakers, right? And of course, we also find a lot of variation. And well, our next step should be to check whether these peaks, these variable peaks, are significant or not. I'm starting then from English in order to check that. Here we have a list of all the significant results, and I'm being very lenient here. I'm also considering the marginally significant results as well, because we had few data collections. 12 data collections is not much in this case. But what we can realize is that all of the peaks that were reached, here we have two examples of, for example, the maximum value for P and the mean value for K. All of the peaks reached, okay, were reached during the instruction period. So in a way, it seems to us that, okay, instruction has really shaken up the system a little bit, right? There were sudden jumps, at least in these cases. In all of these cases, the peak occurred during the instructional period. Well, we were expecting that, but what would happen to French and Brazilian Portuguese? As a hypothesis, we thought, well, the system is gonna be shaken as well. But as we consider that the first data collection also presented high VOT values, would we find something else? We actually did. We actually did find some fewer peaks for French. What is interesting to mention here is that these peaks are a subset of the peaks found in English, right? And except for the mean values for T, significant peaks in French do not precede those in English. So what do I mean? First, they had instruction. While they were having instruction, they had their peak, they reached their peak levels in English. And then a little bit, 1 or 2 data points later, they started showing, peaks or abrupt changes in French as well, right? What would happen to Portuguese, which is a very stable language? That's their first language, especially because they've been living in Brazil. They are not living abroad. They had instruction in English here in Brazil. Well, we also find some abrupt changes, some significant peaks. What is interesting to say is that we find a significant jump, but we also find significant falls. So let me try to explain this further, okay? The first thing that I think we have to consider is that, once again, these peaks found were a subset of the peaks found in English, okay? we have to consider that the peaks for minimal p-values and peaks for mean t-values were also found in French. So they were found in the 3 language systems, okay? What is interesting is that in the 2 other languages, we had significant jumps. Here we had 2 significant falls in T, okay? And they occurred after instruction was over, okay? So in this way, the initial state of the peak was a state in which VOT values were high, and then all of a sudden VOT values went down. And actually, the last collection shows that they got lower than the previous VOT values that had been found in data collection 1. So that's very interesting data for us, because it suggests that, okay, the system somehow is being affected by the other systems, but it's not following the same trend. Actually, the system is trying to deflect from what's going on in English. In English, VOT values are going high, right? In Portuguese, VOT values are decreasing, as if the system, as if the Brazilian Portuguese subsystem were trying to deflect from the other pattern in order for the whole system to have 3 or at least 2 different categories. You know, one category for long lag VOT and one category for short lag VOT. So I think the most interesting thing here is the fact that our significant falls, they are actually deflecting. They are going in opposite direction from that one found in English, right? And of course, we noticed that because we had data collections, 12 data collections. Instruction actually finished in the 9th data collection. If we just had provided an immediate post-test, we wouldn't find this result here. So once again, we have some sort of evidence to show that it's important to keep on analyzing learner data throughout a longer period of time in order to see what's going on in the system. So making this long story short, right? Instruction seems to have contributed to developmental jumps in English. This was also reflected in French, which also showed sudden jumps, and they were a subset of those found in English. In Brazilian Portuguese, there was an abrupt jump in ta right after the one in English. As for t, there are significant falls which occur after the instructional period. The final data collections present lower VOT values than the initial ones, okay? And once again, I insist, an immediate post-test would not be able to show that. So in other words, the Brazilian Portuguese subsystem seems to be deflected from the English subsystem, right? But the 3 systems, the 3 language systems, or the 3 subsystems of this larger language system are being affected. Our second study, we had a male participant, as I've just said. He's Argentinian. He's 36 years old. He was 36 years old at the time of the data collection. He had been working as a professor in Brazil for 3 years and 7 months at the time of the data collection started, right? As for his proficiency, English was his second language, but his proficiency in English was a 2. But he was highly proficient in Brazilian Portuguese, according to the CELP-BRAS exam, which is the official test that we have here in Brazilian Portuguese. He had the highest grade, which was a highly advanced. And of course, he worked with Portuguese every day because he works at university, okay? Here there are some mistakes, not 4 data collections. We have 24 data collections, okay? Every 15 days, right? So we started collecting data in October 2018 and finished in September 2019, right? And once again, following the AXA paradigm, pronunciation instruction was provided from weeks, from data collections 10 to 15. he had 12 classes every Friday, to be more precise, okay? As for the reading instruments, we use the same ones that had been previously employed in Pereirão 2017, so that we could have some sort of comparison as well. And currently, we're analyzing F1, F2, and durational values. But in this paper, we're going to be focusing only on durational values, all right? We haven't finished F1 and F2 yet. Why is it important to focus on durational values? These are data from Pereirão, from native speakers of the language, of the two languages, who took the same experiment, right? You can see that vowels in Porto Alegre, south of Brazil, Porto Alegrense Brazilian Portuguese are much, much longer than the ones found in River Plate Spanish, Buenos Aires Spanish, right? So one of the things that Argentinian learners of Portuguese learn at first is to make length distinctions, okay? Sometimes they don't even make, height distinctions or quality distinctions, but they stick to the length distinctions all the way through because it's easier for them to perceive, right? So we would like to see, based on these results, whether instruction would help them out in at least develop larger vowels in Brazilian Portuguese, right? So this is our data. So we have here this table with the initial values from the first data collection. And we also have some data from Pereirão, comparing that to monolinguals, right? So we can see that there was, when we first started collecting data from him, there was still room for improvement, okay? And we actually, when we look at the whole data set, we noticed that there was some improvement. There are some peaks here, especially in weeks 8, 9, 10. We just have to see whether they are significant or not, right? But what I'm trying to say is, at first, there seemed to be some room for improvement. As for English, well, we also find some increase as he progresses in the data collections, right? Once again, we have to see whether this is significant or not, but there is a length increase as well. And as for Spanish's first language, we can also, at least visually, we can find some increase. What is interesting to say is that in Spanish, if we consider his initial data collection and the data obtained from monolinguals, he was presenting larger durational values right in the first data collection. The only vowels in which he did not present higher durational values than those found from monolinguals were for vowels E and U. But we noticed that there was some sort of increase. Now we have to see whether the Monte Carlo simulations showed an increase or not, okay? As for Brazilian Portuguese, well, we found only one peak for the E vowel. And at first we were kind of frustrated because we thought, okay, we really believed that instruction would help him out. But then we realized that this peak took place before instruction started. And then we were thinking, okay, maybe it was too late to apply instruction. He had been living here for 3.5 years, right? Maybe he has already shown his peaks, okay? Maybe his system now is more stable, right? But we were still able to find one significant peak for E, which is a vowel that he has always struggled in order to make the distinction between the E in Brazilian Portuguese and E sounds, right? But there was only one, and this peak was found before instruction. As for English, we found no significant peaks, okay? And then we were really, really frustrated. We were asking ourselves why. Well, if we analyze the raw data, we noticed that there was some increase, but this increase was not picked up as significant, right? We wonder why this happened. Maybe because he doesn't speak English that much. He hardly ever speaks English. He attended classes at the time of the instruction in Portuguese. He also attended classes in English, but maybe that was not enough. But at the same time, we noticed some increase in the rational values, okay, but not significant. Well, when we saw these data, we thought, okay, we have found only one peak in Brazilian in Brazilian Portuguese, and only one peak in English. So we're not going to find peaks in Spanish. But to our surprise, we found 4 peaks. Okay, 4 peaks in the 4 vowels. And as you know, Spanish has 5 vowels. So the only vowel that did not show a peak was A, right? To our surprise, all these peaks took place at the same moment, okay? So the top of the peak was at the data point that corresponded to the moving average of data collection 6 and 7. So that was before instruction. So that was not affected by instruction. That occurred before that. But this for us is evidence that, okay, his system is, changing in time. Okay, so why haven't we found peaks for Spanish or for Brazilian Portuguese, for example? Probably because they had occurred before we started collecting data. So in a nutshell, summarizing all the data that I have presented, as for the third language, Brazilian Portuguese, we have found only one significant peak in the mid-vowel E, although there was still room for improvement when we compare that with the data obtained from native speakers. And this peak occurred before instruction started taking place. We asked ourselves, well, why haven't other peaks been found in Brazilian Portuguese? Well, it might be the case that abrupt changes took place before the first data collection. That is, this learner was too advanced when we started collecting data from him. He had been living here for 3 years, 3.5 years. We haven't found any significant peaks in English. Those sudden jumps have not been found. Some increase in relative duration can be found in his learning curve. Okay, not significant, but there was some increase that we can see in the graph. In the participant's case, English is not commonly used by this learner, and I think this might be a factor. Honestly, he hates speaking English, loves speaking Portuguese, right? So, I mean, there is also this kind of usage and emotional factor that might be, taking place as well. So summarizing everything, continuing. As for L1 Spanish, to our surprise, we found significant jumps in 4 of the 5 vowels. These significant jumps also took place before instruction in Brazilian Portuguese took place. After these abrupt changes, the rational values kept higher than the initial state. So we should ask, how come we have found 4 significant jumps in L1 Spanish, right? Which should be more stable, but only 1 jump in Brazilian Portuguese, the third language. Once again, it might be the case that abrupt changes took place in Brazilian Portuguese, but before our data collection, okay? Especially if we consider that he'd been living in Brazilian Portuguese in Brazil for, almost 4 years. So we have found a methodological challenge here, okay? We should have collected data from him, when he had probably moved to Brazil or a bit earlier, so that we could find, the peak of his changes in the new language he was in contact with, okay? The results on the English data suggest that language usage may also play a role in determining significant peaks. However, some non-significant increase was found after an instructional period, okay? We ask ourselves, okay, we have found some increase in the descriptive data, but we have not found abrupt changes, or at least not significant abrupt changes. We ask ourselves, what if we apply other statistical methods, just like the change point analyzer that Laura is going to discuss on Friday, right? Are we going to find some phase changes or something like that? Okay, we have not found peaks, but maybe with other methods, and there are many of them, we may find very interesting results there. And this is part of this larger research project, to discuss our data through different means, through different methodologies of considering these long-term developmental data. So just to conclude, I'm finishing right now. So we had two different studies. They were different in its essence because in Schereschewsky 2021, instruction was provided on the non-dominant language to English, and they had been living in Brazil, okay? And this resulted in peaks in the 3 subsystems. On the other hand, in Adelaide Santana, instruction was provided on the dominant language and on the language of the country where I have been living for a while, okay? If there were abrupt changes in the system, they took place before our data collection, okay? We haven't found any abrupt changes for English, although some differences, or at least some visual differences may be found after the instructional period, okay? What is interesting to notice is, at least in Schereschewsky data, this is quite clear. First, there was a change in the language of instruction, the second language, then there were changes in French, and then the first language was the last one to be affected, okay? So there seems to be a longitudinal order in the way that the language systems are affected, right? And of course, the first language should be the last one. In Adelaide Santana, I was not able to find changes in the L2 system, but at least we know that there were abrupt changes somewhere in the L3 system, okay, which might have preceded those found in the L1. Were there abrupt changes in the L2 before my data collections? I don't really know, but the fact is that his durations in English are not that high. They are very similar to the Spanish pattern, so I don't think so, right? So in other words, there are many challenges to be overcome when we get to this methodology. We have to refine this methodology a bit, and we have to consider other things, okay? I think we all should start collecting data as soon as possible, right? And in longer periods, I mean, 1 year sometimes may not be enough, 12 data collections are definitely not enough, okay? So we should have more data collections with spontaneous data as well, okay? We have that in our larger project. We have spontaneous data. We haven't been able to start working on that, but we have that, okay? We surely need to try new methods of data analysis. And I think we have to try to, through these new methods, we have to try to capture the connection between the L1, L2, and L3 more clearly, because although I've been discussing some sort of connection between the 3 of them, at least in this method, I've been running Monte Carlo simulations in one system, the other system, in the third system, and then I'm assuming there's a connection, but the Monte Carlo simulations do not provide me with a clear connection between among the 3 systems. We should also try different measures in each data collection. So as Laura did, mean values, minimum values, maximum values, so on and so forth. Okay. So there's a vibrant research agenda, which we have just started to pursue, but that's a very exciting thing, in my opinion, because it shows that, okay, languages or language subsystems are not separated. They are sharing that common space and they affect each other. So despite all these limitations, it now seems even clearer to us that languages in a multilingual system work as the 3 musketeers. Okay, they're one for all and all for one, right? Or as we say in Brazilian Portuguese, mexeu com uma, mexeu com todas. Okay, so there will be consequences in all the language systems if I'm trying to affect one of them. Okay. These are my reference, and thank you very much for your patience.
So thank you very much, Ubiratã. not only for the interesting talk, but also finishing in time so that we have a space or time for questions. Thais, would you like to conduct the questions, please, with the other
Yes.
participants?
Yeah, how long do we have for questions?
Well, it's 1:55 now. We have 5 minutes.
Yeah, I thought it was 5 minutes, so let's try. Anybody has a question? Eleonora?
Open your microphone, Eleonora. Happens.
Hi, Dita, how are you? Well, my question is always the same. Why not formant measurements and why not normalization? As you know, in order to infer something about vowels, I think formants are more reliable in these inventory differences. I think would be shown much better by formant measurements. And also this is recurrent in our community here in Brazil. People don't normalize durational measurements, and I feel this is a problem for the comparisons. How have you been dealing with that?
Eleonora, let me tell you that we have these measures. We have already carried out these measures, and our paper on formant values has already been published. Okay, that was published last year in Estudos Linguísticos e Literários journal from Universidade Federal da Bahia. Okay, we have carried out this study on the Brazilian Portuguese development part. Okay, with F1 and F2 values, right? And now we are moving on to a second stage in which we're getting the 3 language systems, F1 and F2 values and durational values as well. And this is Anderson Santana's trabalho de conclusão de curso. And we're also writing a paper. So we have these values. I just didn't focus on format here because of time constraints, because I cannot focus only on F1. If I have to talk about F1, I also have to talk about F2. And then I would run out of time. But we have these values.
And sometimes even F3, that was
what
I was wondering about. Much better than. Thank you.
But it has been published.
Anybody else?
Rafael,
you are not looking at the chat because I put something in the chat and then I think
I'm
that
sorry, Rafael.
Yeah, and I think that Ronaldo has a comment.
Ronaldo has a question.
Please look at the chat, please.
Yeah, I'm checking it now.
Thank you, Rafael.
So Ronaldo?
Hi, Bita. Thank you very much for the talk. It was very interesting. You know, this is something we've been talking about for a while, right? The need for longitudinal data in our field, right, to analyze L2 development. And I'll make just a comment and a very small commercial, okay? So the comment is towards the challenges that you have in the end for data analysis. One of them is analyzing the 3 languages at once, right? So, well, at the moment, I think that things like hierarchical regression models, multi-level models, right? Or structural equation models would be something good to model longitudinal data, because then you can add the 3 languages at once in the model. And if you use hierarchical models, some people call them multi-level models, you could use the time of data collection as one of the levels. So you could see the peaks you're looking for in the Monte Carlo simulations. You could see them by having time as one of the levels. And you could include data from all languages at once, right? And especially if you then use a Bayesian approach, you could have this uncertainty also included in the model, right? So this is the comment, and the little commercial I wanted to say is that Ubiratã, Rosane, myself, and other colleagues, we have been concerned about having longitudinal data, L2 longitudinal data. And in the Abralim conference that is coming next week, we're going to have a roundtable about L2. And I'm going to talk about a project that Bira, myself, Rosane Silveira, and Clerton Barbosa, a project we have to collect. We have already started collecting to collect longitudinal data of English L2 spoken by Brazilians to make it available for all researchers. So if you're interested, it's going to be a roundtable in Interabi. So that's it. Thank you, Bira.
Oh, thank you. Thank you. And thank you for your suggestion. Yeah. This is the first study that I carry out with the 3 language systems, because the others were being carried out with Brazilian Portuguese only. But I agree with you. We have, as I've mentioned, we have to go after something that connects the 3 systems. Although the literature does what I've been doing, I'm not happy about that yet, because there isn't a connection. I mean, there are 3 different calculations for each one of the system and a theoretical assumption on that, which I think is valid. But at the same time, I would like to try and explore other methods, so we could talk later on. So thank you very much.
Very good. Anybody else?
Yeah, I had 2 questions, but I think I'm not being
Oh,
able to
go
ask
on
them.
one quick one. You can fit in.
A quick one, yeah. So I choose one of the 2. So thank you, Bira, for the talk. Very, very interesting. And I'm just wondering. I'm not familiar with this domain, and I don't know the works, of course. But I think I missed something when you started at the beginning. My question is very simple. Why is the peaks, so the presence of peaks, so central to your theory or to your study? That's what I'm asking is, if it looks like you are disappointed when you do find peaks, even though you find movement, you find change during time. Why are peaks so important? What do they mean?
Well, in this analysis that we've been carrying out, we are focusing on peaks only. I mean, on Friday, we're going to concentrate on another analysis that does not concentrate on the peak itself, okay? What does the peak mean, okay? A peak in this case would imply a sudden jump, okay? So that would imply variability. The sudden jump may be indicative of a phase change, of a different stage in L2 acquisition. Is this necessarily guaranteed? No. Sometimes a peak is just a peak, and it's not precisely a phase change. Okay, but at least in this method that I carried out today, we are after peaks. That's why when I was looking at the English data, I was commenting on that. Okay, there were changes. There are things there. They're not peaks, but maybe they progressed in maybe a more linear way, or at least on a slower pace that did not allow me to find sudden peaks, right? Peaks in this case, they mean the sudden jumps, which may be indicative of a new stage in language development, okay? But this is not necessarily guaranteed, okay? So, I mean, sometimes we have peaks and we don't have a new stage, right? And sometimes we may have a new stage and not have peaks, okay? That's why this is part of a larger thing, okay? Which, for example, I have actually other, for example, this change point analysis for this very same data, and it will show changes for the English system, okay? Although there were not peaks. There are certain changes and increments which show that there was some sort of progression, of some significant progression, but it was not abrupt, okay? So, but in this methodology that I've been following, I've been after peaks to see if there are sudden jumps that show like the chaotic state in which the learner falls into. Okay, I'm in a very specific stage. Okay, I'm going to another stage, another trajectory stage, but in between, maybe I go through chaos and then I show some sudden movement, which would be the peak.
Okay, thanks.
Just one little comment.
Yeah, go on.
Bira, thank you for your talk. It was really great. But my comment goes in the same way that Rafael did. Why don't you have a lot of data explaining the initial stage difference that you see from weeks 6 and 7? So this is very important because you see in all of your data this movement. And if you look at the just peaks, actually you were not modeling what's more important in your data. That's the change in initial stage. So I think that you should look at that more because you have some kind of stability after week 6 and 7, and then you have instruction after week 8 and so on. And this also makes a difference on the stability that you have on vowel duration and consonant duration. So also initial stage and also instructions make difference on the learning. So this is very important because you have in all your data. So after that, after instructions stops, you have a lot of fall. And I don't see that it's very important to continue a lot of data collection because we already have important conclusions and important results on what this language acquisition does in your initial stage. So I think if you focus on modeling that, it will be very great to explain how a language impacts very early in the development. That's my comment. So of course, if you want to,
can you go and try to finish, Magnum, because we're running out of time.
Okay,
just ask a question.
And it's not a question, just a comment. And I think if it's your goal is to modeling a long period, it will be important to collect more data a year or more. But if it's not, it's just modeling how language affects each other. This 12 or 20 data collection sessions are pretty interesting to your results, I think. That's my comment. Thank you, Bira. It was really great to learn from you.
Okay, I think there are two things here. Okay, may I, please?
Yeah, go on quickly and then.
Okay, I think there are two things. This is one of the techniques that we've been using. As I showed in the beginning, we have at least 3. Okay, we also have moving correlations, and we have change point analysis, which Laura is going to show on Friday. So on Friday, we're going to be showing the same data from Schereschewsky, but through change point analysis. All right. And you're going to see that the results are going to be quite different because we're not going for peaks. We're going for different calculations of the cumulative sum of each one of the moments. Okay, this is the answer. So the first answer. So I think let's wait for Friday so that you can see, for example, other things that we can do with the same data. Once again, as Ronaldo has just mentioned, we can do many things with these data. So not only these 2 forms. Secondly, as for the large or small number of data collections, the literature says that we should go for larger data collections, especially when learners are in a stage in which they are really learning the new pattern. For example, I agree with you that maybe in this case of this learner who's been living here for 3 years, I wouldn't need more data. But if I had gotten him when he got to Brazil, I would need to have daily data. Okay, I wouldn't have to have 500 data points because every day counts, right? So it also depends on the time window and not only the data collection, but the time window that I'm going to be actually collecting data from. I may have like 360 data collections in 1 year, or I may have 12 or 24, okay? And it depends on the kind of learner, okay? So since he hasn't shown many sudden changes, maybe not, okay? But the ideal situation would be to have him right from the beginning with more data collections.
Good. Shall we close here? Thank you very much. Bira was great. I had a few questions I'll write to you and then we talk. Hani, will you take over from here now? I don't think Hani is.
No,
yeah.
I
so you
can see
take
me.
over. All right.
Well, thank you very
Okay.
much, Ubiratã. We took 15
Thank
minutes instead of 5, but now we have the second day of the mini course given by João Vítor and Adriano. João Vítor, are you there?
Yes, I'm here.
So, João Vítor, I will not spend any more time because we are short of time. The audience is yours. So in the first day, João Vítor talked about the acoustical part of his analysis. Today he's going to talk about visual data together with acoustic data, which is something really interesting. João, the audience is yours. You can start.
Okay, thank you very much, Hani. Hello, everyone, once again. I would like to begin this second day by just remembering that all of the data that we are presenting here has been sent to you, I guess, by the organization of the event. So any questions that may have rose from Tuesday to up until now are welcome. So if you have any doubts about what we discussed Tuesday, now would be a good time to ask any questions, to remove any doubts. But we can also maintain this communication further, because this team is not, we are not done working on this team still. So it's not like this is something we did like 1-2 years ago when we don't work on it anymore. So we're still working on it and trying to improve on what we've done. So does anyone have a question from Tuesday? If not, then I'll continue, I'll go on. So Tuesday, I spoke about the acoustical data that we have, but I mentioned that our study was audio-visual or auditory-visual. So now I'm gonna talk a little bit about our visual data. And this nice figure shows us a couple of dimensions that we want to analyze. So we are basically dividing the movement into two: the movement of the head, displayed by these green arrows, and the movement of the face, which is displayed by the small red arrows. So the movement of the head is the movement of the rigid body. So when everything moves together. The movement of the face, it concerns more localized spaces. For example, the eyebrow, the cheeks, the lips, the jaw, or those more localized regions. So we're dividing the movement into head and face. And I hope that's clear, but we can discuss it further. Okay, so how did we record our data? The data was recorded, as I mentioned, by Dennis Burnham and his team in Australia. But the device that was used was the OptoTrack, advised by the NDI company. It is not continued anymore, so people are not building more OptoTrack devices, but it was widely used. I think it's still widely used, but in the future, its usage may diminish, mostly because of the new computer vision techniques that are also presenting themselves as a good option for these visual studies. But in our case, the OptoTrack was used, and the OptoTrack is this device that tracks the movement of LED emitting markers, which are attached to the speaker's face. Okay, so the device basically tracks the movement of each marker. So if we place a marker here on the lip, we are tracking how the lip moves over time. Okay, so that's the idea behind using the OptoTrack. But there's a trick, because we are trying to measure the movement of the head and the movement of the face. But they interact between themselves, right? So when you move your head as a whole, you also move your eyebrow. So we need to separate between those two movements. So for that, in addition to the markers attached to the speaker's face, we have some markers attached to a helmet, which does not move except when the speaker moves its head. So the movement of these four markers here, they depend solely on the movement of the head, whereas the movement of all other markers, they depend both on the movement of the head and on the movement of the face. Okay, so this is a problem that we need to overcome, and this is how we did it. We had the raw data from our OptoTrack recordings, which was, as I mentioned, the position of four markers attached to the head here that depend only on the movement of the head. And we have the position of every other markers that depend on both the movement of the head and on the movement of the face, the facial muscles and articulations. So the solution for that is a technique called head motion compensation. And it involves a little bit of mathematics that I'm not gonna go deep into right now. But this technique allows us to separate the movement into the movement that depends only on the head and the movement that depends only on the face. Okay, on the end of the presentation, I'm going to provide some more references on this topic and some more general references too. Okay, now we have our acoustical data and our visual data. And how are they different? Okay, so let's go back to Tuesday and remember our acoustical data was the F0 contour of our tokens, of the words and syllables that were spoken. So when we're speaking about acoustical signal, we are speaking only of how one variable changes over time. So there's only one variable we are concerned about, and this is the fundamental frequency, F0. Okay, when we're talking about the visual signal, it is a little bit more complex because, first of all, we are dealing with head movement and we are dealing with face movement. Second of all, we are dealing with space. So we have 3 dimensions, the axis X, Y, and Z. So multiply everything by 3. So it's everything is 3 times more complex. And third of all, we are not controlling the changes in only one variable. We're controlling the changes of all markers. So here we have 29 markers attached to the face, and each marker moves in 3 dimensions. So we are tracking the movement of each marker in 3 dimensions. And we are also tracking the movement of the head in 3 dimensions. So instead of having only one variable to be concerned about, as we had in the acoustic signal, now when we are dealing with visual data, we have, in our case, 87 variables for the face signal and 6 variables for the head signal. So from 1, we jumped to 93, 6 plus 87. And that makes our analysis a little bit more complex, even though the core of it is still the same. Okay. Why is this a problem? So why do we always run from data which are highly dimensional? There's one term that's been widely spread in the machine learning community. That is the curse of dimensionality. And one might think, as it's written here, that the higher the numbers of variables there are available for me to provide to my model, so that the model may learn and make better inferences, that's the better. So if I have more variables, my model will be better. But that's not always the case, okay? Because if I just keep adding features, adding markers, adding dimensions, some of those features, some of those markers, they may not be truly related to what I'm trying to measure here. In our case, some of those markers may not make a difference when we are discussing lexical tones, okay? And this is one thing that we should always have in mind. It's not about the size of our data, always. We should first have data that we know that is significant, and we shouldn't be worried about that before we are worried about the amount of data that we have. And also, some models deal better with high dimensional data than other models. For example, Tuesday, I presented 3 models, the KNN, the LDA, and the SVM. We're going to see shortly that those models, they behave differently when they are presented with high dimensional data. Okay, so the choice of the model also has an impact here. Okay, now I'm gonna bring another topic on statistical learning that I didn't mention on Tuesday. On Tuesday, we mentioned about training data, about test data. So we need some data to train our model, and we need some data to test our model on, okay? So those two terms need to be clear, training data and test data. Okay, but why do we develop those models? Ideally, we develop those models so we may deploy them and use them to predict real data, okay? Imagine that I want to build a device that will analyze a video of a people talking a tone language that has no sound. I want to design an application that could, in real time, detect what lexical tone the person was speaking. Okay, so this is one kind of application that we need to think about when we are working with these machine learning models. So, how to measure a model's performance? The performance of the model, it's not best measured by how well it classifies the data it was used to train the model. Okay, it's like you're studying for a test. You have all those questions that the teacher made available, so you can study to the test, okay? And you read them all night long, and you know them all. You know all the letters of the questions, you know all the answers, okay? This is you learning. You are using the data that is available to you, so you are learning, you're making connections. But the test is something different. It's something different. The test is composed by other questions that are different from the ones you studied the night before. So if you only know the questions that you studied, you will fail the test because your knowledge will be very limited, very specific to the data that you learned. But if you learn in a more general way, and if you were able to make general assumptions that generalize to other questions that are similar but not the same, you will do well on the test, okay? Because you were able to make connections that are general, that serve for new data that is still unknown to you, okay? And we can do that, we can divide, like I said, our whole data in training and test. So we can train the model on one part of the data and test the model on another part of the data that is still unknown, okay? But we can do that in an even better way, okay? And there's this technique called cross-validation. And there's a cross here. I don't know if the name comes from this cross because this is only a representation, but it sure has something to do with it. So here we have our data set repeated 5 times, okay? It's just the same data set represented 5 times. At first, I'm gonna divide the data set into train and test, okay? I'm gonna divide it into 5 parts, which should ideally be the same size. And I'm gonna use 4 of those parts to train the model. And I'm gonna use the remaining parts to test the model, okay? And I'm going to repeat it 5 times so that each of the parts were used as the test data at least once. So this way, we're gonna test the model in 5 different settings with slightly different training data and with different test data. And this is a way we can assess how well our model works, which is more robust than just dividing once the data into train and test and doing this analysis only once, okay? I could go on more about the topic of how we can evaluate machine learning models, but it is very, there is so much to learn, so much to talk about, that I'm gonna leave some references at the end of the talk and we could always discuss it later, okay? Now I'm gonna go on to the code that is a little similar to the code I presented you yesterday. I'm just gonna share my other screen here. Can everyone see it?
Yes.
Yes.
Okay, thank
Yes.
you very much. Since this is a script, I'm gonna run some preliminary lines here, like I did Tuesday, okay? Getting some necessary libraries. By the way, this library, Carrot, is one of the main libraries that we can use to apply machine learning techniques in R, okay? So if you are working with another language like Python, there are other libraries, but in R, I know this library Carrot, and it's widely used and it's well maintained. So this is a suggestion. Okay, now we're gonna perform the polynomial fits. Since you may remember from Tuesday, we are parameterizing the data by fitting polynomial curves to all of the data, okay? So for instance, this is gonna take a while because Tuesday we had only one dimension to think about, okay? But now we have more than 100 dimensions, close to 100 dimensions to think about, because we have all of our markers and how they move in 3 dimensions each. So this data is larger. This data is composed of more numbers, of more variables. So it is more difficult for us to work with it. It's not impossible, it's just more difficult. Okay, now we're gonna take a look at the head movement, the recorded one and the polynomial approximations that we did. Okay, let's run and see the graphs. Okay, they're here. We have the rotation of the head and the translation of the head in each of the axes, okay? So as you may see, the blue and the red line, they are almost the same, which means that the polynomial curves that we are using, they are flexible enough to capture how dynamical the movement of the head is. Okay, so we are not losing that much information here by using our polynomial approximations. We are just gaining the benefits of it, which are making all of the signals the same length, which is very important, and also that enables us to describe our data with 4 coefficients, which are the polynomial coefficients, and that is very good for us. Okay, now onto the phase movement. Also plotting what we recorded and how well do we approximate it. Okay. We have the movement here in the x-axis. We have the movement of the jaw, movement of the neck, movement of the right eyebrow, movement of the upper lip. Okay, so you can see also that both curves, the blue and the red, are very similar. So the polynomial approximations are also more than enough to capture how dynamic those signals are in time. And we can notice here that, for example, the right eyebrow is at a larger, at a higher position than the jaw, then the neck, and then the lip. So it does make sense, right? The right eyebrow is at the top of the head, or at least above the center of the head. The upper lip is a little bit above, and below that there's the jaw, and below that there's the neck. We notice that it moves a long time, but the movements are in millimeters here, so they're not very well represented here in this graph. Also on the y-axis and on the z-axis, okay? So just the fact that we need 12 images to represent our data, and we're not even representing all of the markers, just shows that we are dealing with data that is highly more dimensional than the F0 data we dealt with on Tuesday, okay? Now I'm going to create some data frames to perform the classification. And we are going to see here also a huge difference, okay? We are going to see that I'm going to press here to run, and it's going to take a while, okay? That is why I have prepared, I have already some results to show you so we can discuss, and then we're going to come back here and see if it has already stopped to run, okay? I'm going to just change my screen here. Let's see. Okay. These are the data. And here are the results, okay? Those results are presented in box plots, just as we saw on Tuesday. And those results are how well the SVM classifier worked on the data, okay? So the SVM classifier is the classifier that is a little bit more complex than those other two. So it should be able to handle high dimensional data better, okay? Let's see. What can we see from this graph? Let's just remember what we saw on Tuesday. On Tuesday, we saw the random signal here, which had an accuracy of about 16%, which was expected since we have 6 different classes. So we are just guessing lexical tones by chance here. And we have the F0 signal, which provided us with an accuracy of around 75%. Okay, so that's our baseline. That's how well we can classify lexical tones using the acoustical information, which is how we are used to, okay, how we are used to describe it theoretically, and how we are used to talk about lexical tones by their F0 contours. But we also see that we achieve high accuracies based on the movement signals, on the visual signals, okay? So the lexical tones are also present in the visual information, and that's the most important information that we have from this work. There is some information about lexical tones in how our face and our head move. It is systematic in a way that we can train models to predict lexical tones based on it. We just need to study it more so we can be more certain about which specific movements of the head and which specific movements of the face are more important for this task, okay? So, for example, here we have 4 different signals. We have the head signal, which is the movement of the head, and we have the face signal, which is the movement of the face. Then we have those 2 signals combined here in the signal face plus head. So it's the movement of the face concatenated to the movement of the head. So we have a signal that is a combination of those 2 signals, okay? And then here we have our more complete signal, which is the movement of the face, the movement of the head, and the movement and the F0, which is not a movement. And this signal is a signal that emulates what we see in a real world conversation best. Because when we are talking to someone, we can hear the people, we can see the person, okay? So we have all of the information available to us to make our predictions. So first of all of the movement signals perform way better than the random signal, and we perform some statistical tests, and this difference is significant indeed. So there is the systematic information about lexical tone on the visual information. Okay, about differentiating the visual signals, we were able to classify between lexical tones better with the movement of the face than we were able to classify them with the movement of the head. This may be something that happened with our speaker, because there are also studies that are showing results that say that the head movement is more important than the face movement. So this is still an open question, but once again, I'm going to repeat it. What's most important is that all of the signals achieved accuracies significantly higher than the random accuracy. When we combine face and head, we achieve slightly better results than only with face, but not significantly better. And when we combine all of the signals, we achieve an accuracy that's near the ceiling here of around 80%, okay? So this is very interesting, because many questions may arise from this graph. Is there a ceiling from what we can achieve with machine learning? Should we do perception tests to see how a person would be able to predict between lexical tones in a similar situation with similar stimuli? So this is a work that we did, but which also opens many doors that are there to be explored, okay? Now, let's return to the R Studio and see if it has already run. Share screen. Okay, it has run. I use the LDA here. So let's see how the LDA behaves. The LDA behaves here quite similar to the SVM. I'm just gonna leave the KNN running here so we can compare that too. I'm gonna run with the KNN and analyze the graph here, okay? While the program is still running. With the LDA, we also have a ceiling here, but the ceiling here is around 70%. And we also notice that these two signals are more close to these two signals. So the models work a little bit different as we've seen, okay? But the general tendency remained the same. The head movement performed worse among the visual signals, but all visual signals performed statistically significantly better than the random signal, okay? And it is nice that we can get those same results by employing different models, because it shows a little diversity in our methods. Of course, there are many other methods that we could use, more specifically with high dimensional data. I think many of you have already heard of neural networks, and those types of models are able to deal with high dimensional data better than those simple models that we are using here, okay? But that also demands more computational time, that also demands more data. So it's always a trade-off between what you have and what you may achieve with that. Okay, now just to finish here with the script, I'm going to present the results that the KNN method achieved, okay? And the KNN method was not able to achieve a good classification accuracy with the visual information, okay? They are all very close to the random accuracy, but a little higher than the random accuracy. And one thing that also makes this interesting, okay, KNN uses the F0 signal and achieves good results, around 75%. The F0 signal is here too, okay? The F0 signal is still available here, but the KNN method was unable to classify it as well as with only the F0 signal. What's the difference here? The additional data, which is very high dimensional. And as I mentioned before, there are some models that behave better or worse with high dimensional data. And the KNN model is one of those models that suffer from the curse of dimensionality. It doesn't perform well with high dimensional data. And this is because, here's some text that you may read on the material that we made available, but I'm gonna change to the KNN slides that I had so we can be more illustrative. Let's go back. Okay, the KNN is based on finding distances between points, okay? We all know that finding a distance between 2 points in 2 dimensions is quite trivial, okay? In 3 dimensions, okay, we can see how it works. It is quite visual for us, how we can measure these distances and see which are the nearest neighbors, okay? So the number of the method has the word nearest, which has a very close relation to distances. But if we have more than 100 dimensions, it is not that clear to differentiate between the distances, okay? We can still calculate the distances with the aid of the computer. That's not a problem. We can get a number for the distances. But since there are so many dimensions that are into this distance, the distances, they tend not to differentiate well between each other. So it's very difficult for this specific method to tell classes apart when there are many dimensions. So this is why dimensionality reduction techniques are so used in many, many applications. And I'm not gonna go into this right now, but just so you can get a name in your heads, one of the most used techniques is the PCA, or Principal Component Analysis. And this goes right in the same direction that we were using here, okay? Adding features that are not truly associated with making predictions will impair the model's performance. So what does the principal component analysis makes? It tells you which are the principal dimensions of the data, which dimensions are more relevant to the data, and which are not that relevant. So you can use only the more relevant dimensions of your data and leave a lot of dimensions that may be only slowing you down aside. So this is one of the techniques. It is not that complicated, mathematically speaking, but it also demands some linear algebra. So people can apply it with only one line of code, but if you want to see how it works, it takes a little bit of mathematics, but it's not that complicated, principally to get the idea, okay? So this was the message that I wanted to present to you. So the results of our work. The related literature here on statistical learning, as I mentioned, there's this book by James and colleagues from 2013, which personally helped me a lot to understand those core principles of statistical learning. And I think it is written in a very accessible language. So you don't need to be an expert in engineering or a bachelor in engineering to understand it. It has many figures, it has many real life examples. So it's a good book to get an idea of how this method works, of how these methods work. Also, a literature that is highly related to what we presented is one article that we published 1 year ago that presents basically the method that we outlined here, but in more detail. So this is open access, so feel free to access it. And those are the other references that I mentioned along the presentation. So that would be it, Hani. I'm open for questions now.
Very good. So, keep your screen shared.
Okay, I'm gonna keep the PDF shared, but I may also change to the RStudio if necessary.
Sorry for the dog.
No problem.
It was silent until half a minute ago. So thank you very much, João Vítor and Adriano, for the talk. I hope I expect people could see the power of statistical learning, and in addition, to learn how visible and acoustic features from speech can be measured and analyzed in a coordinated manner. So we have time for questions. It's 10 to 3, so that's perfect. So any questions?
I think Ronaldo has a question, a quick question.
I have to see the chat.
Yeah.
I have Ronaldo, please go ahead.
All right, João Vítor, thank you very much for the workshop. As I said yesterday, it was very clear and very interesting for me. It's not really a question
the day before yesterday, not yesterday.
Right, the day before yesterday, right. It's not really a question in the sense of questioning you, it's just a curiosity about the acoustic data and how you guys decided to fit the curves. It makes sense using the polynomials, and just a curiosity, have you guys thought of using splines, and do you think that splines would do the same trick as the polynomials, or it doesn't make sense? Just a little curiosity of using splines versus polynomials to fit the curves.
Okay, we didn't think about splines, but I think Adriano could maybe come in and...
Splines are a special class of polynomials, right? If I remember well, when I...
Yeah, it's a concatenation of polynomials, right?
So where you make the points to coincide, the derivatives to coincide as well, so that you have smooth functions. They are useful when you have to concatenate polynomials smoothly. Adriano, please go ahead. Sorry, I interrupted you.
Well, I mean, we could, but I think we don't need them. I mean, I think the polynomials worked fine. One thing I like, well, the idea of using polynomials came because, you know, we're inputting all these tokens to the model, and they have different lengths, which of course are based on their duration. So it's more like a normalization of the input vectors, right? So if we define that a polynomial has to have a certain order, like fourth order, third order, whatever. So all of them, regardless of their lengths, are going to be represented by that given number of like parameters. So in that sense, no matter how long they are, or like what their durations are, they're now the same length, in the sense that the length now is the vector of coefficients behind that polynomial, right? So they're all like 4 coefficients or 3 coefficients. A nice side effect, I think, of the polynomials is that we can, by using them, we can impose certain constraints, right? So for example, if we use like a second order polynomial, right? Like, and then we are imposing the constraint that that curve can only have one inflection point. And if we use like a third order polynomial, we're imposing the constraint that that curve can have only 2 inflection points, right? And I think that fits nicely, because when you look at those curves, they actually have that kind of behavior. They can't do anything they want, right? They're like, if you have level contours, which are basically like a straight line, and sometimes you have like one inflection point, right? So yeah, I mean, that's basically the reason for using polynomials in the F0 case, right? And since we are using them for the F0 case, we also use them for the visual data, right? So the primary reason it's like normalizing the length of the input vectors, that, you know, the vectors input to the models, and for the F0 case, I think we have this nice side effect of imposing constraints. We could certainly use the splines.
Makes total sense. Thank you very much.
Yeah, but Ronaldo, just to add a little bit on that, Adriano's response was like, we looked at our data and we saw what was enough for us. If we had different data, for example, intonation curves along one sentence, maybe a polynomial wouldn't be enough. And we would need an S-spline, or we would need a higher order polynomial. So it depends on our data.
Yeah, that's right. Yeah, these are very short, you know, segments. So yeah, that makes sense.
Okay, thank you.
You're welcome. Thank you.
So any more questions? Ronaldo, okay, wrote it here. Or maybe you should ask for, so João? No.
Hi.
No, just to be sure. One thing. So, if we don't have a question specifically to talk, could you tell us why are we studying tone languages?
Why are we studying tone languages?
Yes. Oh, it's a language, right? It's one language, not.
Yeah. My answer will not be the whole answer, but it would be part of the answer. Tone languages are widely spoken around the world. And I think the linguists who are here may agree with that. And we have many speakers, a large number of speakers. But most of the studies that are made, they're not done on tone languages as much as they are done in non-tone languages. So there's this unbalance between
something that is always intriguing to me is that why don't we have most of the languages as tone languages? Because it's some feature that is very easily included in speech, and in spite of that, we don't have so many tone languages. So many languages are not tone language. That's my question. Maybe one of the linguists here in the audience could discuss about that. Why don't we have most of the languages as tone languages?
It's too hard, Hani.
It's too hard what?
To learn.
Well, not for them.
I don't think because it's too hard. It's because languages differ. You have tone languages, you have stressed languages, and that's the way it goes. You don't have to have a tone language to have a language.
Yes, I remember a sentence that I read in a book from Schroeder, who said he quoted something like, language is a gift of God, except for Chinese, which is the invention of a very wise man. Or that was the sentence.
In his jokes.
It's not a joke. That's a real sentence. And I asked myself, why did he write this? And I still ask it to myself, and I don't have the answer. Okay, so as we are still ahead of time, and unless we have more questions, somebody wrote something here. Wait a minute. Language variation, Hani. Okay, Adelaide. So if we don't have more questions now, we can stop for, let's say, 10 minutes and come back for the talks in the afternoon. Is that okay?
Yeah, Hani, I would just like to make a final comment. I just find very interesting these, lots of these tools, like they've been applied to, well, in this specific case, right, to this lexical tone language problem, but I think they could be applied to many other areas. I saw an email from Maria. I apologize, I haven't answered yet, Maria. I saw it, about a possible application for that. I mean, these methods are general, right? They could be basically used in very different scenarios, I think, right? I mean, historic linguistics has focused on the acoustics because, it's the main modality. It's because it's simpler and all the tools are there, right? But I think like this kind of tools and techniques, they open many possibilities. So I think it's quite interesting, and more people are paying attention to this now. I'm actually glad to see that.
Yeah, because we have data from two different domains, and we could parameterize both of them into one single matrix, and we could process them together.
Just like yesterday, who was it? Like there was this talk using Bayesian statistics, which I found very, very interesting, right? Not many people use it.
Ronaldo, right?
Yeah, I think it was Ronaldo, right? I mean, yeah, I found that extremely interesting,
At the end now, I'd like to emphasize the last thing that João Vítor said, that this book that you can see there, Statistical Learning and Introduction, this book is really not difficult to read. Things there are put very clearly. And these statistical learning tools are really, really useful for us to analyze and get insight in many of the data that we acquire. So,
and also, very important, this book is
freely
it's
available.
available in the internet. Maybe, João, if you can put the link in the chat.
Okay, I'm gonna put the link in the chat.
Okay. Okay, so let's stop for 10 minutes. We start at 3:10, the next session of the meeting. I will close my microphone and camera now.
Okay, see you guys soon.
Hi, is there someone from the organizing committee here already?
Yes, of course.
Hani, I would like to ask you, I have two colleagues that are interested in attending this latest sessions today, the oral presentations, but they have not registered for participating.
Tell them to register. The form is open.
Okay.
And send them the link to the Zoom session.
Okay, thank you very much.
You're welcome. And so it's now time to go on. Adrielle, are you there?
Yeah, I'm here. Are you? You can hear me, everyone?
You, but I cannot see you yet.
Okay.
Do not worry.
Here I am.
Would you share your screen with us?
Oh yes. Just a minute. I hope it works. Are you seeing my screen?
I can see myself in your screen.
Oh, okay. Here.
Okay. So
now it's okay?
Yes. It's 3:12 now. I think most of people have already come back. If let me do as yesterday by sample. So Adelaide, are you there? No, let's wait.
Yes, I'm here.
Okay.
Sorry.
Then this it's okay. And the next sampling, Priscilla, are you there? No. So let's wait one more minute. Let me try one more. Ronaldo, are you there?
Yes, I have just arrived.
Okay. So what do you think? Can we start? I don't know how many people are really there. That's the problem with these virtual meetings.
Yeah.
If we were in a real room, we could see the audience, and if the audience is there, we can start. But because I'd like to start now because otherwise we are going to finish too late. I think I will start so Lais. Okay, everybody's saying, so people are here. Good. So the next session is from Adrielle Santana. She did this work with Adriano Barbosa, with Rafaela Bossier, and I myself. And she's going to talk about relations between behavior and neurophysiological representations of speech phonemic units. For those who are not used to this kind of measurements, it will be a quite interesting work to understand this kind of relation. So Adrielle, the audience is yours. You have 15 minutes.
Okay. Good afternoon, everyone. My name is Adrielle, and I will present a work I developed in my doctorate named Behavior and Neurophysiological Representations of Speech Phonemic Units. I was advised by Professor Rafaela Bossier, Professor Hani Camille Yehia, and co-advised by Professor Adriano Vilela Barbosa. So in this presentation, I will begin with an introduction. Then I will talk about the methodology for the time domain analysis of the data and the results. Then I will talk about the methodology for the time frequency domain processing and then the results, and finishing with the conclusions. So many studies showed that we perceive the world around us by categorizing the sensory input. This was a study, for example, for the perception of emotions, colors, and speech. Here, we have a continuum of faces representing emotions, going from angry to disgusted. At some point in a categorical transition here, someone will begin to categorize the emotion as being disgusted. This categorization also happens for colors. Here, for example, at some point, someone will begin to categorize the color as being orange instead of red. And we have this categorization also for sounds. In this study from Lieberman et al. From 1957, we have a continuum with syllables b, d, and g, with variation only in the second formant frequency. Here we have a categorical transition where someone will begin to perceive the sound as being a d instead of a b. It's important to note that the position of these categorical transitions here for the color, here for the emotions, they may be different depending on the person. Each one of us will have one position for that. But how this categorization happens in our brain? For centuries, researchers investigate and try to understand how our brain processes speech. In the 19th century, it was proposed a neurobiological model in which we will have an area responsible for speech perception, the pharynx area, and another for speech production, the Broca's area. In the 20th century, several models for speech production and perception were proposed, as, for example, the motor theory of speech, the quantum theory of speech, the hyper and hypoarticulation, the analysis by synthesis, just some examples. However, these models do not try to explain the neurobiological mechanisms that underlie the production-perception relationship. With the advancement of technology for acquisition and processing of brain signals, several studies try to propose a neurobiological mechanism. An important one is the dual stream model, where brain structures in a dorsal stream would be responsible for mapping the sensory representation onto articulatory motor representations. And ventral structures would map the sensory representations onto lexical conceptual representations. But how these models relate or explain the speech categorical perception? Some works try to address this question. We saw in those works that some of them used passive listening tasks, while others use active identification tasks. Some used continuum based on format variations, including one specific with a very strange continuum going from U to A, while other works used a continuum with a time-based acoustic characteristic of the phoneme. Some works analyze responses in the time-frequency domain, while others just in the time domain. We also saw that these works measured data in different areas of the brain, and also they have different conclusions about how much time takes for the phonemic categorization happen after the stimulus onset. So we propose to investigate the neurocorrelates of categorical perception of speech sounds. And based in our literature review, we saw that attention influences areas recruited and the speed of the categorical perception. So we proposed to perform an experiment using a passive listening and an active identification task. Also, we saw that acoustic cue influences how the brain processes speech. So in our experiment, we used two different acoustic cues, one based on time and other based on frequency. So voice onset time continuum and the format continuum. We also saw that in those works, the choice of continuum was made a priori. So we decided to do the choice of the stimuli based on the categorical transition of each participant. We also saw that different areas of the brain give different responses. So we performed measurements in the frontal and temporal areas, as well as the left and right areas. And none of those works performed a dissociation between the physical and psychophysical characteristics of the stimuli. So we propose to do that. In order to perform this dissociation, we will consider the following hypotheses. Here, we have a psychometric curve, which relates the physical characteristic, here the VOT of the stimulus, with its perception, which is represented here by the probability of perceiving the stimulus as being a ta. So for example, the red stimulus here is physically a ta and is 100% perceived as being a ta. We hypothesized that it's possible to identify two separate axes in the neurophysiological space, one related to the physical characteristics of the stimuli and another related to its psychophysical categorical perception. The neural representation of ambiguous stimuli, here represented in yellow and green, here in the middle of the physical discriminant axis, will be closer to each other, the representations will be closer to each other if their physical characteristics are similar, while in the psychophysical discriminant axis, for example, the yellow stimuli will be closer to, if it is perceived as being a da, its neural representation will be closer to that of the blue stimulus. And the same for the green and red one here. So we performed an electroencephalogram acquisition in 11 subjects, high-handed, and measured the signals from those electrodes here, the CZTP9, CZTP10, CZF7, CZFC, and CZF8. Experiments were randomized across participants, and each participant performed both tasks, the passive and active, with both continua, the VLT in the format. In the acquisitions, we selected 5 stimuli based on the psychometric curve of each subject for each continuum. So trials were averaged by participant, task, continuum, electrode, and stimulus. We measured the magnitudes and latencies of the N1 and P2 components of the event-related potential, performed ANOVA and contrast analysis of the factors that presented significant effects. In an exploratory analysis with the grand average, we can observe that we have different differences in the evoked responses depending on the stimulus, task, continuum, and brain region. But with the contrast analysis, we could evaluate in relation to the cortical region that there is a left hemisphere dominance for speech processing, that a spectrotemporal analysis of the acoustic cue happens at the temporal region, and generators for the N1 and P2 components are more laterally localized. In relation to the acoustic cue, we saw that formats and VLT evoke different behaviors in N1 and P2 generators. And related to that, the N1 is sensitive to the VLT variations. We also saw that stimuli are processed differently when there is attention to the task. In relation to the ambiguity, we saw that ambiguity is reflected into the event-related potential amplitudes. So when the ambiguity increased, we saw a decrease in the N1 P2 magnitude. We also saw that the P2 component may code the ambiguity or maybe the effort for the perception of the ambiguous stimulus. In relation to attention, we saw that attention influences the generators recruited to process stimuli and also influences more left hemisphere generators than the right ones. And attention also influences the speed of stimuli processing. It's interesting to evaluate how the brain oscillations are involved in the coding of different acoustic cues and tasks. So we evaluated if the time frequency domain, how those dimensions influence the physical and psychophysical neural representations of the stimuli. In general, we want to relate the behavior, which is observed in the psychometric curve of each subject, with its neural representation. So we organized the trials by electrode, participant, stimuli, continuum, and task, resampled, and then we performed the discrete wavelet transform decomposition at 9 levels. This was important because in the last levels, we obtained a frequency band similar to that of the main brain oscillations, the delta, theta, alpha, beta, and gamma. So to perform the relation between behavior and its neural representation, we arrived in a high dimension, low sample size problem in regression, where we had only 5 observations for 800 wavelet coefficients. To address this issue, we developed for this work a regression technique named regression on low dimension expanded input space, RODSIS. Then we were able to obtain the physical and psychophysical discriminant axes for each subject, continuum, and task. We evaluated the axes in 2 ways. First, through the angle between them, and second, through the distance between them, which we call it discrepancy. So we can evaluate how significant is the difference between the physical and psychophysical neural representations of the stimuli for different conditions. With the angle, we compared how it relates with the slope of the psychometric curve, represented here by the red lines. In some studies, this slope is reported as being proportional to the categorical perception of the person. Here, each black dot represents one of the 11 subjects. The results for this analysis are represented here. The positive correlation indicates that a stronger categorical perception relates with a more distinct physical, psychophysical internal representation. Those distinctions are represented by the angles, where here represented by the angles, they were greater for active than for the passive tasks. Here the active, here the passive. And also they were greater for the VOT than for the formant, acoustic cue. This may show that different processes in our brain are coding each acoustic cue. The red stars here show the cases where the correlation was significant. For the discrepancy analysis, we worked with its value in different regions of the scalegram. The scalegram is the time frequency representation of the discrete wavelet coefficients. Here, we selected 8 regions based on the N1 P2 latency and on the theta, alpha, beta, and gamma bands. For each region, we obtained the mixed effect model with the factors feature, which is related to the continuum, type, which is related to the task, and the electrons. Then we performed the ANOVA and the contrast analysis of the significant effects. As a result, we observed a more lateral location of the speech structures, that the gamma activity observed in our regions probably related to the integration, synchronization of these regions. We also saw an enhancement of the alpha activity with attention. We observed larger discrepancies associated with the temporal region than with the frontal medial one. And that brain oscillations involved in high-level speech processing present stronger activity as early as in the N1 component time frame. Concluding, observed stronger responses and more discrimination in the temporal region. We observed a left hemisphere dominance. We verified the formant frequency principle. If you want, I can talk more about that after. We observed an early distinction of acoustic cues, a more distinct physical, psychophysical neural representation for VOT than for formants, and for active than for passive tasks. We saw variations in electrode responses depending on the feature, type, and the region in the scalegram. We saw that mechanisms of categorical perception depend on the acoustic cue and task. And then a neurobiological model for speech perception should consider these factors. We also saw that participants which categorize better have larger difference in the internal physical and psychophysical representations of the acoustic cues. And we saw that the event-related potentials reflects behavioral information involving all the frequency bands analyzed here and in early and late time frames for the speech processing. The scripts used in this work are available in those repositories in GitHub, and my theses are available in the UFMG repository in this link here. Thank you.
Thank you very much, Adrielle. The talk, I think it was possible for most people to follow at least the first part. The last part has a lot of interesting results that could not be explained in detail because of lack of time. But I thank you for finishing in 15 minutes exactly. So we have time for questions.
It was difficult.
So let me check the chat here. So Ronaldo said it's interesting. You have any questions, Ronaldo? So one thing that I know this work in detail, but I can ask you a question that arose to me during your talk today. In this case of the behavioral part, the angle. So can you come back to the slide where you show the angles? The thing that I was
here,
that even in a very high dimensional space, two things that do not depend on the dimensionality are the distance and the angle between vectors. In this classification, the angle is something in this this angle. So although it's drawn here in 2 dimensions, it could be in any kind of dimensions. When you said that the formant principle was preserved, and what is the formant principle?
Oh yeah, it was verified. So this formant principle, it's some authors observed that when the first and second formants of a vowel are closer to each other, the any1 pitch2 amplitude is greater than when they are more separated. So that is the formant frequency principle. They believe that it has to do with some generators inside the brain for those formats.
Okay.
And this is more for vowels.
So just a moment. Eleonora wants to make some comments before she has to leave. So Eleonora, open your microphone.
Yes. Thank you very much, Adrielle and co-authors. This is great work. I recognize Kelso and many other authors that have predicted this kind of results, but in a more intuitive approach to dynamical systems. This is the way you put it is is a great contribution to the problem of categorization in our field. And I want to congratulate you and of course Hani and Rafael. I must leave now, but I'm sort of trying to catch up, taking a look at the videos every day. Thank you. Bye-bye.
Thank you very much. Thank you.
No, one very simple thing, Adrielle. Can you say again da and ta? Can you speak these words again?
Oh. Da and ta.
Yes, I heard ta in both cases. I don't know if it's the channel or something.
Oh, maybe my microphone or your phone.
No, or the channel or the speech encoding. I don't know. So anyway, so
da.
One important
I have one
thing.
comment, Hani.
Okay, Adriano.
It's not a question. I don't know if it's just me, but at some points I had the impression that I was like listening to synthesized speech because of the prosody Adrielle was using. I don't know, maybe it was just me. Very interesting.
It was okay. For me, it was okay. Really okay. But one important thing now. So yesterday, so for all the audience, this is important. We have made available the recordings of the sessions from Monday, Tuesday, Wednesday, and we are going to make all of them available at YouTube. If any of you have any concern about that, please let us know. But we believe that making the talks available to everybody will be something good. The link is, so Leonardo can send the link later so that everybody can see. And the talk of Adrielle and all of the talks today will be available as well. And then for those who are interested, we have a paper published explaining the technique. And also we have the whole thesis of Adrielle, which gives more detail about the results. I think we could just a comment, what you call discrepancy.
Oh, yes.
Is an Euclidean distance.
It's the Euclidean distance. Yes, the calculation is the squared, and then the, let me show here.
It's a kind of Euclidean distance.
Yes, yes. It's the distance between the point of the vectors, if you can imagine that. It's like,
so
I have
Leonardo
to
has just put the YouTube channel link in the chat. So for those who want to see, and
actually this is playlist.
I said okay.
But you can search for Eicefala in YouTube, and it's easy to find.
Aha, good to know. And I think I can call now the next talk. I think it's Melchior.
Yes, I think so.
Mm-hmm. So Melchior, can you make? Thank you very much, Adriano.
Thank you.
In English, I say Adriano instead of Adrielle. I don't know why.
It's for French, maybe.
L2. So Melchior, please make your screen Please share your screen.
Okay. Can you see my screen right now?
Not yet, but we will.
Oops, I think I must allow. Just a second. I try again. Can you see now?
Yes, now it's perfect.
Okay.
Experiments on speech analysis in near ultrasound using conventional audio equipment. So recently, Melchior and we have carried out research about some kinds of spoofing and attacks in using ultrasound. That's what Melchior is going to talk about. But one interesting thing is that the same techniques that he used to generate and acquire ultrasound could be used by any of us to check if we combine that with event-related potentials or evoked potentials, could be used to check if human beings are or not able to perceive ultrasound, even if we cannot hear them. This is not craziness. For some reason, some people believe in that thing. So we could check it out to confirm or not if it happens. But I will not steal time from Melchior. Melchior, you have 15 minutes to present, and the audience is yours.
Thank you very much, Hani, for the introduction. So our work have some also some motivations. We're going to talk about an attack that is dealt in virtual assistants, and that's a more practical way of using the whole linguistics studies that we have. And so smart devices, they're used for recording and reproduction of audio, and they can go far beyond the limits we use in our everyday lives. But these capabilities have been used maliciously to attack virtual assistants. And nowadays, this kind of service is widely available in smartphones, in our computers, and now we can even turn on and off things at our homes. We can ask for Alexa or Google to turn on our flights. We can, and nowadays, we are introducing, the technology is introducing a concept called smart homes, that we can even control via internet our homes from the virtual assistant. So we can lock doors, unlock doors, allow someone, oops, I am on vacations and I must allow someone to go to my house to get something for me. I can do this remotely, for example. And this rise of permissions that we give to virtual assistants has raised concerns in security. And so several attacks in relatively new area of study emerged from this, revealing a very innovative ways to execute arbitrary commands in a targeted device. So the first point we must discuss here, can the audio recording, reproduction, and virtual assistant device. Well, the microphones that we find in our computers, in our smartphones, they are able to record sounds above 20 kilohertz, and the speakers in general, they are able to reproduce sounds above 20 kilohertz, limit for our auditions. And devices are not ideal, and they are subjected to imperfections. And these characteristics are the ones that are used in these attacks. So here we have an frequency response chart of this microphone, one of we used in our experiments. And we can see here in the y-axis that we have the response of this microphone, and we have the frequency in the x-axis, and we can see that we have not a roll off in the end here of this chart. What that means that we have some response of this microphone in the near-ultrasound frequency range. And so we have the first question: can we record and reproduce ultrasound? And the answer is yes. The short answer is yes. And here is a small scheme of our experiments. We used an audio interface that was configured correctly to reproduce and record ultrasounds, and connected to an audio monitor, a mid-low end studio monitor that is very used in music. It is about $200. About nowadays it's 180. So, and we recorded ultrasounds being reproduced through this audio monitor in smartphones and in microphones. And we use this signal, a time stretched pulse. The important thing here is that it is a signal that goes from 0 hertz to 96 kilohertz. And it has constant magnitude through time, and its frequency grows linearly through time. So we have this signal, and we applied it to microphones and smartphones. And this is the response we got from one microphone, a bearing, the Behringer that we showed. I'm sorry, another microphone. This is a better one, that we were able here to record even above 80 kilohertz. So we were able to reproduce and record ultrasounds, and we have some crazy phenomena happening here that we're going to talk a bit later. And in a smartphone, we were not able to record ultrasounds here. We can see that our smartphone were able to record up to 24 kilohertz because they are not projected. They're not designed to record above this frequency because it's the frequency used in audio, in video equipment. When we record a video, the audio goes up to 24 kilohertz. And here we don't have anything. This here is a native phenomena. It's a noise, okay? And it was audible. It was not our ultrasound that we intended to hear. To record, I'm sorry. So we applied the TSP in a condenser microphone and a MEMS microphone, the kind of microphone that we find in this in our computers, in our smartphones. And how does these imperfections works? Because how they work? Because they play a very important role in this attack using speech. Well, devices are not ideal. They're subjected to imperfections. And a perfect device would be linear, a constant response and the whole spectrum. And this does not exist in the real world because of physical limitations. And distortion is introduced because of physical phenomena that happens in the transduction process. That is, when we try to transform a pressure wave of our speech and a voltage that can be interpreted and processed inside our smartphones or computers. And this affects the distortions. They affect the whole spectrum, including near-ultrasound signals, if we set up our reproduction recording system to support it. And the more intense the signal, the more distortion occurs in the transduction process. And here we have the curve that transforms an input from an acoustic pressure, that is a sound wave that I am speaking right now to you through my computer, and my microphone is converting my speech to a voltage in millivolts that it's being processed, recorded, and sent to you via internet. And it does have an equation that models this kind of distortions that happens. And we have two kinds of distortions: the harmonic distortions and the nonlinear distortion. The nonlinear distortion is the one that make this attack possible. And how does distortions, I'm talking about a lot of some crazy things, I think so, but I'll get to the point. How these distortions can bypass a virtual assistant, because this attack, we cannot hear it. It is an ultrasound. Can we feel it? We don't know. That's the discussion. But if we craft a special signal, we can make our smartphones understand and process the sound that we want, and bypass the virtual assistants. They think it's a real voice command, and they execute the command. The microphone is able to record the signal in near-ultrasound, and the distortion phenomena takes place in the microphone. The speech recording is translocated to its conventional frequency range after it is processed from a pressure wave to a voltage wave. So in the middle of this process, our speech signal, it appears in a frequency range that can be processed and understood by our microphones. So if you craft a radio-like signal containing a speech recording as a message, we exactly like an AM radio that we can turn on at our homes and listen. The information of the envelope of our speech signal is maintained, it's preserved. So when this process happens, this distortion process happens, our virtual assistant can understand the envelope of our speech and process and recognize as a real speech signal. And the signal, the AM signal, it's a short for amplitude modulation. The important thing is it is transmitted by a carrier, a wave that whose amplitude is varying accordingly to our signal. So we have here a signal, a simple sine wave, and we have here below in red our amplitude modulation signal that is changing its amplitude accordingly our signal. So our envelope of the signal is preserved, and this is very important. And we tried some attacks and some prototype commands. This is one of them, the main one. What time is it? We didn't want to do anything bad to the virtual assistants. We just wanted for research purpose. So we used just this attack, this what time is it? It's not harmful to anyone. So this is the command recorded, and this is our AM signal. We have a carrier, and this whole signal is changing its amplitude, containing our signal twice in an upper band and a lower band. We don't need to enter in details here, and it will be more clear a little bit later. So again, we have an input in Pascal and an output in millivolts. And if we process this kind of wave through our model of distortions, when we do the math with the system, we will result in this M of T. And M of T is our message. So when we get an input of this signal, this AM signal, specially crafted with a command that we want to execute, through this equation, our message will appear in the spectrum, and the virtual assistants will be able to reproduce it. So to exemplify, we have here 2 kilohertz per tone. We are going to modulate it in amplitude modulation. Here it's our AM signal, or amplitude modulation signal. Now, this is, I'm sorry, here there is an error. This is a pressure wave, okay? Here below, it's a pressure wave, not a voltage wave. Now we're going to transduce it to a voltage wave, to a tension. And here it's our distorted signal passed through that equation that I showed before. And we can see that the red signal, it is not symmetrical. Look, its maximum goes to 40 millivolts here in red, and below it goes to about minus 45 millivolts. So it's not symmetrical. We introduce the distortions. So when we see the spectrum of the signal, we can see our original message. It's on its original location in the spectrum here in red, and in orange, and above of it, the distortion resulted in the process of the conversion. we applied the signal to smartphones to measure if we can indeed apply this attack into the device. So we put a carrier with a message, our 2 kilohertz sound, 2 kilohertz sine wave, okay? And it goes from 12 kilohertz to 48 kilohertz, that is ultrasound. And the result when we put in smartphone to record the signal is that we have here in orange our original message. We have a carrier in the middle, that is our AM signal. The AM signal is this, okay? This in red, it's all the distortions that happens in the microphone because of the transduction process. And here below in green, we have our signal, our original signal that made able us to attack this virtual assistant and recognize our sound and our speech signal in the device. And here in dark red now, we have the distortion that still appears and it's not propitious to our attack, okay? So here, where we do not see an attack, the ultrasound is indeed being reproduced, and our demodulated message is appear in our device. And we could indeed reproduce and attack the smartphones to answer this ultrasound that our ears, we humans cannot hear, but our smartphones could execute. And that's it. That's it, the short resume. And one important thing that I didn't say, the name of this attack is dolphin attack because it is in ultrasound, and dolphins, they communicate with each other in ultrasound below the water. So they call this attack as dolphin attack. So the next steps for this research is a more in-depth analysis using capsular coefficients to evaluate better the regions of executions and role of the distortions into the effectiveness of this attack, because this other distortion in dark red, it's not propitious to our attack, okay? And other thing is the use of concatenative synthesis to analyze the effectiveness in arbitrary speech commands. We like a hacker that type into his or her computer the attack he wants to execute, and it will attack your targeted device. And the last thing, exploring other attacks and variations with using other technologies such as neural networks or other modulation schemes. There are lots of very creative attacks that we can study using speech and communication theory. So thank you very much for your attention.
Thank you very much, Melchior. We have time for 1 or 2 questions. So you can think for the audience. The application that Melchior showed is basically a kind of attack that really exists. But I wonder if you don't have questions about the first part, which is basically about the possibility of producing and recording ultrasound without any equipment that is not on the shelf. So, Melchior, I have my question. You have very good audio equipment, right? So,
yes. Can
you tell us what was the speaker that you used?
Yes, it was an KRK speaker. I think I can show it here. Don't mind the mess. Can you see it?
Yes. Okay.
It's a mid-range speaker. There are lots of better speakers. Okay, but it was able to reproduce sounds up to 40, 50 kilohertz in a not very intense signal. But we have applied a very intense ultrasound signal in order to record up to 80 kilohertz.
I will tell here to the audience an interesting story that happened to me in 1996 when I was at ATR in Japan. I have to remember the name of the scientist. I think it was Tsunoda, but I'm not sure. He asked me to be a subject in his experiment and asked me to be in front of a plasma TV. By that time, plasma TV was something really expensive. And there was a hi-fi audio playing gamelan music from the Bali Island. And I had to listen to that music for 3 or 4 minutes. And then he would play again the same music in front of the same TV. But then he asked me, when did I relax more, the first or the second time I heard the music? I didn't know anything what was happening, but then he told me later that in one of the cases, he was reproducing music using a band-limited signal up to 20 kilohertz, which is the limit for human auditory system, of the human auditory system. And in the other case, he played music up to 70 kilohertz, which is near ultrasound. And what he found out is that from 200 subjects that he took, something like 130 or 140 said to be to have relaxed more when they heard the signal not band limited, but going up to 70 kilohertz. And he was trying to show evidence that somehow human beings could perceive ultrasound. I don't know if he is or if he's not right, but this kind of experiment that Melchior has shown is a way so that we can check it out and see if there is or not any perceived acoustic information beyond our hearing limit. Well, that's it, just to think. And we are still in time, which is good. I think I will. Okay. Are there questions? Okay.
Yeah, just a small question, just to be sure if I got it right. Common loudspeakers like the ones we have on our cell phones, are they able to reproduce ultrasound or not? Do we need something special?
Not to reproduce, but to record, right?
Okay.
Okay.
Well, we have not tested the very small speakers such as the ones we find in smartphones, but we know that small speakers less than one. I don't know the measurements. I forgot, but small speakers can indeed reproduce with the correct intensity of sound voltage. Okay.
Okay. But for your experiment, you use your special loudspeaker, right?
Yeah, it's not that special. It's
yeah.
potent. It's very potent. Yeah, we applied above 120 decibels of sound pressure.
Okay. Thank you. We can discuss more later.
And Adelaide commented here, could it be a resonance phenomenon? I don't know. I don't know. But it's an interesting point. We will check it out.
Okay,
I think.
Thank you.
Thank you, Adelaide. I think we can move to the next talk. Carla, are you there? Melchior, you can close your screen.
Hi, Hani. I'm here.
Okay, Carla. So the next talk is from Carla Vasconcelos, and she's going to talk about fatigue and sleepiness in aviators, analysis of voice, speech, and language variations. Basically, she's going to speak. Carla, be welcome. Please share your screen. That somehow it's possible to detect fatigue and sleepiness based on the frequency and distribution of some speech time features like articulation index and pauses and things like that. But I will let Carla do it, but your screen has only, okay. So make it full screen, Carla.
Yes, can you see my?
I can see your screen. With but there is something, please close, there is some tab that is covering part of the screen.
Yes.
Make it full screen for you. Just click on the full screen button in your PowerPoint.
Yes, but
Carla?
no problem. So,
make it is it full screen for you? Because here we can see we cannot see it full screen. It's covered somehow.
it's covered. Problem with my computer, Hani.
No, it's not the computer, it's something else. Try to...
Carla, if possible, try to share your home screen. It may be something that is above the screen you're trying to share.
Okay, now nothing is covered now. Now make it full screen. Perfect. Okay, Carla, you can. It's perfect now. You can start. Yes, you can start.
Oh God.
You have 15 minutes.
Okay. Good afternoon, everyone. My name is Carla Vasconcelos, and I will present to you the results of my PhD research. And I'm a speech pathologist and audiologist, and I had my master's degree in linguistics and my PhD degree in neuroscience. And Hani was my advisor at UFMG. And the subject of my study was the impact of fatigue and sleepiness on voice and speech and language. And before presenting the results, I will briefly talk about what the scientific literature defines about my subject of study. According to literature, human fatigue is a physiological state which causes reduction in mental or physical performance, decreases in alertness, inability to operate safely work functions, and tasks that require continuous concentration. And it causes excessive work, stimuli information, sleep deprivation, prolonged and excessive effort, among others. And the sleep. Sleep is a physiological state, but the 24 shift workers, like pilots, suffer a break in the patterns of the circadian rhythms, and the frequent sleep deprivation generates chronic fatigue symptoms. People deprived of sleep begin to lose the ability to resist the commands from the brain to sleep, even in situations of risks. And according to literature, the alterations related to fatigue and sleepiness, like a reduction of muscle tension and body temperature, can cause cognitive speech playing, respiration, phonation, articulation, and resonance, and radiation. So fatigue and sleepiness induce changes in intensity, voice, frequency, rhythm, pulse patterns, intonation, duration of speech, articulation, and voice quality. So I would like to explain in more detail a definition about voice, speech and language, but I have no time to do that here today. And so I put here a short definitions about the communicative acts and about the parameters that we used in this study. Our communicative acts are divided into verbal and not verbal. In this study, I focused only on verbal acts, like segmental and non-segmental parameters. If you have any questions about this, you can send me an email so I can explain in more details. I put my email in the end of this presentation. In short, the objective of this study was to develop a method for detecting aviators' human fatigue and sleepiness based on acoustic correlates of voice, speech, and language. And the informants of this research consisted of aircraft pilots, all native speakers of Brazilian Portuguese, and neurologically healthy. To this end, this research was divided into 5 sub-studies. In the first, speech samples from pilots complaining suspected of fatigue sleepiness were compared to a control group. The results were also compared to the fatigue avoidance scheduling tool, the FAST. From the second to the fourth sub-study, the researchers analyzed 3 real cases of accident with evidence of fatigue sleepiness as contributing factor in 2 of these, and speech samples of pilots recorded before the accident were compared with those recorded during the crash. In the 5th sub-study, the aviators were screened through 4 fatigue sleepiness scales: Karolinska Sleepiness Scale, Epworth Sleepiness Scale, Samperelli Fatigue Scale, and Yoshitake Fatigue Scale. And speech evaluation was performed in 2 situations: on a day off, when they were not complaining about sleepiness fatigue, and during a working day in which they were fatigued sleep. The data from the scales were statistically analyzed using the Friedman test and Wilcoxon test. It was observed that fatigue and sleepiness increased on the working day. For speech, in the 5th sub-study, the pilot GLM was used. 9 variables were extracted from speech: elocution rate, mean pause duration, total pause rate, fluent pause rate, disfluent pause rate, disfluent silent pause rate, disfluent filled pause rate, articulation rate, and total silent pause rate. The first 7 variables showed a significant variation over time when participants showed increased fatigue and sleepiness indexes. In addition, PCA was applied to reduce the extracted variables to 4. It was also found that it is possible to use linear discriminant analysis to group individuals and classify new cases with or without fatigue and sleepiness based on a database built for this purpose. There was quantitative and qualitative variation of voice, speech, and language in 2 out of 3 cases where the accident occurred in the presence of signals of fatigue sleepiness. In the first sub-study, statistical and qualitative variations were also observed between the control group and the group with complaints. I put here an example of audio with some previously described changes in voice, in speech, in a pilot. like excitation, prolongation of vowels, articulation errors, prolonged and frequent pauses, fundamental frequency lowered. So listen.
O dia anterior a esse relato, eu acordei por volta das 10 da manhã, tomei meu café, fui dar minha costumeira corrida, almocei por volta das 2 da tarde. À tarde eu tentei dormir um pouco, não consegui. Me deitei por volta das 18 para tentar dormir, não consegui. 19 também não havia conseguido, não jantei e fui conseguir dormir próximo às 10 horas da noite.
I have no time to detail my results, but I put here another example of my second sub-study.
Rádio da base de Santos, boa tarde, bom dia, Papa Romeo Alpha Falsalva, na escuta?
In this example, the pilot had a higher percentage of speech discontinued, about 42% of disfluency. Here I put an example of my fifth sub-study.
E aí a gente ficou conversando com a Fábio e tivemos a notícia de que a nossa moção mudou. Passar aqui 10 dias, né? Fazendo 5 relativos à missão, tá? Acho que depois a missão com o ministro. E, no entanto,
So through these studies, we found that the acoustics and perceptive parameters of voice, speech, and language analyzed here are sufficiently robust to detect central fatigue and sleepiness. I put here a summary of main finds in this study, like the alteration in temporal organization. For example, we found a reduction in elocution rate when the pilots were fatigued or sleepless or sleepy, a reduction of fluency, a reduction of articulation rate, a reduction of total rate of pause, and a high percentage of disfluence, an alteration of vocal polish. So, thank you for the attention, and I'd like to apologize. I'm sorry for my problem with this computer.
Okay, so first of all, so thank you very much, Carla. Please keep your screen shared with us. Bira, this work was published in a journal that is more directed to pilots and aeronautics. It's time to bring it to the speech community, and in that case, we have to change a little the focus of the work. As you can see, when Carla spoke, many of the things were related to pilots, and pilot is just one possibility. She is now trying to do that with drivers in the same way, because these are categories where fatigue and sleepiness are crucial for the activity. But we have Adelaide has a question, please.
Could you please pass the references then on the chat later on so that we can find it?
Carla, can you make the reference available?
I didn't put my reference here, but I can send to you by mail.
No, but try to put it in the chat.
Yeah, just the chat, just the reference for this specific article. Okay, for the link for us to find it so that we can read it through.
But Adelaide, you have a question?
Yes, thank you for your talk. It was very interesting indeed. I was wondering, what are the next steps? I mean, are you going to, do you intend to make some sort of system, or do you want to provide this study for people to evaluate the fatigue of pilots? What do you intend to do next?
I didn't listen to you.
No, Carla, so she asked what we intend to do next.
Yes, that's it. I was wondering whether you plan to build an automatic system for recognizing fatigue, for example, or whether you are going to provide this study and these parameters for specialized people to use it and try to recognize signs of fatigue and sleepiness in pilots. I don't know.
Yeah, I'm studying I'm in a postdoc now with Hani, and we are studying the possibility of developing an automatically method to measure these signals of fatigue and sleepiness in drivers, not in pilots. If I understand your question, because my audio is not so good, it's very slow.
But do not worry, Carla. So I think you answered Adelaide, and
yes.
And Adelaide really she's working really to trying to make a product that could be used for that thing. And just a curiosity, I was reading a paper published in Physics Today, where they consider what would be an issue in the year 2116, so within a century. And this kind of measurement in the future could be questioned as a kind of probably of a privacy concern. So people could be worried about being somehow invaded with having his or her privacy violated. But that's another point. But the important thing is that really we can detect fatigue and sleepiness. One important point that Carla could have made is that we have to compare a person with the same person. So what is normal for one person cannot be normal to another person. So that's just a point. Anyway, we are still in time, which is good. We can move now to our last session. Thank you very much, Carla. And Adelaide, I think I think it's you again.
Yeah, it's me again.
Good.
Okay.
So it's and we are on time today, which is good.
Yeah.
So we have now our last talk in the afternoon from Adelaide and Fabiano Silva and Vanderlan Alessio de Carvalho and Lourenço Chacon, a generic representation of orthographic structure in texts written by children.
Yeah.
Please, go ahead.
Okay, so thank you, Hani. This presentation is related to the one I presented on Tuesday. And because of that, some things I will say will be kind of a recap. So, but
but they are different, okay? So our motivation is that spelling is taken as a parameter to evaluate whether an individual is literate or not in Brazil. Also, because of that, children are submitted to an exam that evaluates their performance in spelling twice in elementary school at the 3rd and at the 5th grade. As I told you last Tuesday, the last edition of the National Literacy exam held in 2016 showed that 34% of the children evaluated did not achieve the expected scores for them to be considered literate students. So this is a very bad result. Because of that, we intend, or we are already designing a system that generates orthographic forms, such as the ones found in texts written by children from the 3rd and the 5th grade, departing from some patterns of errors. We have also as an objective to offer subsidies for teachers to understand the hypothesis underlying the forms that deviate from standard orthographic ones. And also, we aim at providing teachers resources to evaluate whether or not the errors fit a given grade, so that the teachers can develop some specific tasks for children to fit the grade they are supposed to be in. So the first steps of our work consisted in analyzing data to classify errors and to detect patterns that group them following criteria such as type of error and school grade. We also elaborated a generic representation for orthographic structure in texts written by children. And this is the main point of this presentation today. I will show you the representation we elaborated. But before that, I have to tell you that the representation is machine readable and corresponds to an abstraction departing from real data. As a background for you to understand the notation we propose, I have to tell you that we took as a departing point 168 texts containing more than 45,000 words. These texts were produced by children from the 3rd and the 5th grades, and the selection was not at random. We selected texts from children from 3rd and 5th grade because of what I told you before about the moments in elementary school when children are evaluated. And the texts that constitute the database gathered by Chacon rewrite narratives for children that the teacher of each class read to the students with a specific objective of collecting data for a written language database. Our theoretical background follows Chacon and Pesarini 218. In that work, authors claim that literacy process involves transparent correspondence between graphemes and sounds, and also opaque correspondence. What they call transparent correspondence stands for examples such as the letter F writes only the sound of the voiceless labial dental fricative. On the other hand, what the authors call opaque
correspondence stands for example, the letter X that can write many different sounds. Opaque correspondences are set by conventions that may or may not consider the context of occurrence of the sound. And conventions set spelling rules independent from phonological variation. This is important because we see in the database that some misspelling may result from phonological variation that children put on their writing, but this is not the case, or this is not the point here today. It's just for you to know this kind of thing. So Chacon and Pesarini also claim that there's a gradiency in the relationship between phonic aspects and orthographic system in Brazilian Portuguese. And they conceive that gradiency lies in the distinction between different types of errors. For example, phonological substitutions can be different, involving or not the same classes of sounds. This point may be clearer from the examples I give to you in this slide and the next one. These are the errors, or the type of errors as proposed by Chacon and Pesarini. So they claim that there are transpositions, substitutions, or phonological substitutions, non-phonological substitutions, and omissions. On the set of transposition, we have some subsets like permutation that can be seen in an example as this monoro. So we have here the exchanging of syllables inside the word. And I didn't say this that today, but I said on Tuesday. This is one datum, one example that illustrates our methodological decision to take the orthographic word as the unit of analysis in our system, as all the others that you can see in the slide. On the slide, sorry. Another subset of transposition case is the intrasyllabic one. So we have, for example, Prometeu, that is the letter R should have been put among between P and O, but the child exchanged its position in the same syllable. On the other hand, we can have also an intersyllabic transposition, that is something like amarção instead of armação, where the letter R went from the first to the second syllable in the word. This is not the same case we have when dealing with substitutions. So when we deal with phonological substitutions, they can occur extra some phonological classes. For example, in ninguém, the I letter at the end of the word replaces the M letter. So we have two letters that write different phonemes in the language, but phonemes that pertain to different phonological classes in the language. But we have also phonological substitutions within the same phonological class. For example, fazendo instead of fazendo. There's an exchange between the voiceless and voiced fricative. We also have some hybrid phonological substitutions. That is, we have, for example, chamava, where the X letter
was used, replacing the sequence CH. We have different ways of writing the same sound in the language, but it's not a phonological question properly. It's not, sorry, let's reformulate it. It's not properly that we involve a phonological class or different phonemes. We involve only different letters to write phoneme, the same phoneme in this case. We also can have non-phonological substitutions. For example, esquecendo, wrote the way I put it here. You see that this diacritic cannot in standard forms be used on that context, but the child use it that way. So this is not a phonological question, it's only a question of the convention, the orthographic convention. Finally, we have omissions, like in açúcar for açúcar. Children can delete one or more letters in the word. This was this was a better example. The child deleted more than one letter here. You see that these errors Chacon and Pesarini propose deal mainly with consonants, but we have many errors involving vowels. That's the reason why we proposed some additional classes or types of errors. So we proposed vowel substitutions involving posterior vowels. So for example, we can have preocupe, where the first U letter replaces the O letter that should occur here. We have vowel substitution involving frontal vowels. In this case, we have here in our example, the vowel I after the, or the letter I, sorry, after the letter P replaces the letter E that should occur there. And finally, in this set, we have a random subset. In this case, we had parque, where the letter A replaces the letter O we expected here in porque. We also have what we call combined effects. That is, in the same word, we can have different types of errors. So in vergonhados, for example, we have the omission of the letter R in the second syllable, and following that, instead of the voiceless velar plosive, we have to have the voiced velar plosive. So we have to have the letter G, not the letter C. We also can have insertions, like in the example, hesitava for estava, the inflected form for the verb to be. And we can have other types of errors. It's not a very good label, but we didn't think of another, of a better one. So this one involves prosodic facts, mainly dealing with the word segmentation. So in já vi we have a sentence where everything is written together. We have one orthographic word corresponding to a whole sentence. Well, data analysis allowed us to classify the errors as we exposed, and also allowed us to propose a set of labels and to manually deal with some data in order to verify whether or not the labels would perform adequately. So the labels we propose are crucial for elaborating predictions on errors, and these predictions are related to the graphemes involved in the errors, as well as they take into account information such as syllable internal structure, syllabic boundaries, primary stress placement, stress degree, and consonant class. Here you will have a table showing all the labels we propose. We assign a variable for each label, and we also associate the orthographic representation for each label. As you can see, we have here labels for the consonant classes. We have labels for vowels. And I see now there's a nasalized I missing there, sorry. We also have labels dealing with the position of the unit within the syllable, for example, onset, nucleus, or coda. We also deal with first unit in complex onset or second unit in complex onset. So the position of the unit within complex elements of the syllable. This is also true for nucleus and for coda. Finally, dealing with stress, we propose indexes as the ones predicted by Câmara Júnior. So you have there 3 for stressed syllable, 1 for pre and post-tonic syllable, and 0 for post-tonic final syllable. 2 stands for the secondary stress. So as I told you, variables comprise classes of segments and subsets of consonants based on manner of articulation, as well as subsets of oral and nasal vowels. Variables also comprise the position of each unit within the syllable, considering vowels to be the only possible units in the syllable nucleus. Also, subsets of consonants occurring in coda is smaller than that in onset. So we take into account a phonetic restriction in the language. And variables consider also that there are units which occur in second position of complex syllabic constituent. And we propose a numerical index consonant to that consonant to indicate its placement in a complex constituent. Variables comprise yet prosodic structure of the word by assigning stress levels to the syllable, as I told you, based on Câmara Júnior. So we have the example cafezinho at the bottom of this slide, where you can see that for syllable K, we assign the level 1. For syllable Fé, we assign the level 2, because this is a secondary stress that results from a morphological process in the language. Then we have the level 3 for the primary stress of the word. And the last syllable, I made a mistake here, sorry, must have been assigned the 0 index because it's the post-tonic final syllable in the word. Variables comprise labels for different syllables constituents, such as N for nucleus, A for onset, and C for coda. Labels for signalizing whether the syllable constituent is a simple one or a complex one. And as such, labels allow us to capture and understand how units relate to each other. They also allow us to predict possible sequences, as well as sequences of units that violate constraints of well-formedness. For example, sequences of graphemes that write sound sequences that do not obey to the sonority scale, and also sequences of graphemes that annotate randomized sequences of consonants. The labels indicate segment boundaries with parentheses and syllable boundaries with square brackets. So here you have a labeling for the words, for some words in the data set. These are all examples extracted from the data set. So how do we read the labels? From the left to the right, just for me to go faster, the two syllables are exactly the same. So they have a fricative within a simple onset followed by a vowel. The third syllable has a fricative within a simple onset followed by a vowel and carries primary stress. And finally, the fourth syllable has a nasal within a simple onset followed by a vowel. These labels are machine readable, as I told you before, and correspond to some abstraction, departing from real data. Labels can provide teachers a way to understand the hypothesis children formulate when they make spelling errors, and they can help machine learning to simulate errors children make when during the process of acquiring the spelling rules of the language. Labels do not specify which vowel occurs in syllable nucleus, and this was a problem in the first version of the labels we proposed. So because of because some errors involve vowel qualities, such as rechonchuda for or explodiu for explodiu, we proposed some new labels for accommodating vowel aperture. So we proposed some indexes, 4 indexes indeed. And also we proposed new labels for accommodating place of articulation for vowels. So frontal, central, and posterior. Our next steps consist of implementing the labels in the system, verifying how the system deals with the labels for the words of the data set, and also for additional words we intend to put in the system. And finally, we intend to improve the labels if necessary. So that's all. I thank you for your attention and your patience. And I can answer any questions you have. Thank you.
Very good. Thank you very much, Adelaide. It was a very interesting talk. We have time for questions. Before the questions, I would ask you if, while I was attending to your talk, I was trying to remember which of the errors that you showed here I used to commit when I was a child.
Great.
Can you remember those that you used to make?
I couldn't. Indeed, I couldn't.
Okay, so we have time for questions.
Okay.
Well, so one question at the end of the talk, you said that you don't specify the vowel that is the nucleus of, but it's not so hard to change, right?
No, it's not so hard to change. That's why we proposed the new labels. Mm-hmm. We have already done that. And this is a more complete labeling system because by hypothesis, we can deal with vocalic harmony that we see in the data as I showed you.
Mm-hmm. And one question, it's very natural, this kind of analysis for the Portuguese language and some other Latin languages. In English, would it be natural too?
English is said to be a language where the relationship between graphemes and sounds is less transparent.
That's it. That's what I thought. Yeah.
So maybe they have also, but as we are trying to develop a system for Brazilian Portuguese, I must confess that I did not look up for some similar system in English.
I think it's not natural for English at all, as far as I can understand, but I was just checking with you. But for languages like ours, and that's why when we say, since a long time ago, we teach the beabá, so it's a simple way to teach how to write in Portuguese.
Yeah, you're right.
In English, you cannot say BAB or something.
No. In English, there are those jokes involving possible different ways of writing the same word. You have one famous joke attributed to a writer, I forgot, but you have those GOTI, GHOTI for fish, for example. And they have many other jokes like that. Mark Twain was the author who the joke was attributed to.
Very good. And while I was watching your presentation, I was also thinking about the language that I really don't know almost anything. Quechua that Eleonora said in the first day. I don't know how they deal with syllables, especially because they have the glottal stops and things like that. That in Portuguese we almost don't have, except for the which we still have the glottal stop, and it's natural to say. I try to put the glottal stop in other words, I simply cannot. I'm not able to include a glottal stop in hotel, for example, or something like that. Okay. But I was just wondering how your very interesting work would be used in languages with other structures.
That's a good question. That's a good question. And maybe we have to think about other labeling criteria or something like that, because when we are dealing with syllable structure, the point is that we are trying to provide subsidies for the machine to learn the syllable structure in Brazilian Portuguese. Because departing from that, the system must be able to simulate errors children do when writing apart from the standard forms.
And you have a good corpus to get the natural errors. Another language that occurs to me is Japanese, where we do have almost syllabic system like ours, but the units for them is the syllable itself. You don't have a K, they have Ka, Ke, Ku, Ke, Ko, and things like that. So it's really interesting how things change from language to language, but some things don't change. This orthographic to phonemic transcription is something specific.
But you're right. Some things are universal,
and some are not. It's now 10 to 5. It's a good time to finish today. Thank you very much, Adelaide. And we'll be back tomorrow at 1 o'clock with the second part of the mini course of DDA. And then after that, we are going to have five talks and 5 presentations, and we will have room for a discussion. So I would encourage everybody to try to have a look in the salad. I don't know if you can say that in English. A salad of works that we had here, from things going from physical measurements to some machine learning things, to a lot of interesting things about L2 and L3, and how we could somehow link things together. And I see you tomorrow. Anybody would like to? There is something in the chat. Bira said, thank you, Adelaide. Okay.
Thank you.
Thank you. Thank you, Bira. And I see you tomorrow.
See you. Bye-bye.
Bye.
See you. Bye-bye. Have a good night.
Bye-bye.
Bye-bye.
Bye. Bye. See you tomorrow. Bye.
See you tomorrow.
Hani.
Deixa eu parar a gravação.